Hi everybody, we're Blue Dentist and we're excited to share with you all our Capstone 2020 project. With the explosion of connected electronic devices, wireless security efforts are in high demand. Blue Dentist targets Bluetooth devices, which are traditionally hard to track due to their unadvertised presence and frequency hopping. Blue Dentist utilizes a software-defined radio to collect data from a large band of frequencies in conjunction with an NVIDIA Jetson Xavier to efficiently process the large stream of data in order to provide a user interface which details all local Bluetooth devices and activity. An expandable storage interface allows for long durations to be monitored unsupervised. I'm Jeff, and I primarily worked on the hardware design of the project. In particular, I worked on integrating the NVIDIA Jetson into our design, the high-speed design and layout, and the STM32 microcontroller firmware.
Hi, I'm Chris Chan. I also worked on hardware design and was responsible for microcontroller integration, power management design, and Jetson adaptation.
I'm Griffin Danninger, and I work to develop the Blue Dentist software focusing on the configuration of our SDR and CUDA drivers, optimizing our algorithm, and conducting final testing.
And I'm Zach Battles. I also worked on the Blue Dentist software, focusing on the multi-thread building, the algorithm design for our program, and the open source code library integration into our project.
Bluetooth monitoring presents a unique challenge because devices only announce their presence when establishing connections. After this, connections begin frequency hopping between 79 Bluetooth channels. However, transmissions from a unique master device using traditional Bluetooth are uniquely identifiable due to their stable access addresses. Existing Bluetooth SDR solutions, such as the Ubertooth One, have the bandwidth to cover only a single Bluetooth channel at a time. This makes them great for communicating over Bluetooth, but a poor choice for monitoring. Blue Dentist records data across all Bluetooth channels. When set up in a Bluetooth-rich environment, this enables our program to identify multiple unique master devices by their access address active at the same time, and record their data transmissions over a prolonged period. This could be useful to identify specific offending devices in a secure room that is supposed to be radio silent, or recognize malicious Bluetooth interference activity out in the world.
The project was split into two independent halves, with Jeff and I working on the hardware platform and Griffin and Zach working on the software. Since we are attempting to catch and analyze Bluetooth signals that are operating in the gigahertz range, our hardware needed to be fairly advanced to keep up. The key components of our design are a powerful NVIDIA Jetson Xavier to do the data processing, specialized XTRX software-defined radios communicating via PCI Express, NVMe SSDs for fast data storage, and full I/O for a native Linux system including HDMI, USB, and Ethernet. To support all our components that total around 65 watts of power consumption, specialized power design was needed. We also included a STM32 microcontroller to handle I/O expansion and board-level control for the sensitive power-up sequencing. Jeff will go into detail on our PCB design process.
To deal with the complexity of our design, we created the schematic in a hierarchical layout. The image shown here is our top-level design. You can see the several core blocks to our design in this image: the Jetson, power supply, and STM32 microcontroller. There are additional blocks for peripherals, such as the connectors for the radio, SSD, USB, Ethernet, and HDMI. The connections on this schematic carry groups of connections between the relevant green blocks here. Some of the connections even carry up to 10 signals. Each green block in this image is actually its own separate schematic page. For example, this is a schematic page for the STM32 microcontroller I/O. Each design block, those green blocks on the last page, on our top level schematic contains a separate schematic page of similar complexity. But designing the hardware schematic wasn't even half the battle. The layout turned out to be extremely challenging. Given the Jetson, radio, and SSD, our board size came out to around 7 inches by 7 inches. A 699 pad BGA connector is used as the interconnect between the Jetson and our board. Additionally, the majority of the high-speed connections in this design are concentrated in one section of the BGA connector, which you can see around the center of this image. This required us to use 8 layers in order to break out all of the required signals while preserving signal integrity. These high-speed traces, such as PCIe, Ethernet, HDMI, and USB 3.0, had really strict routing requirements. We had to learn how to use tools to calculate trace width and spacing to maintain the target trace impedance. And to achieve realizable geometry, we needed to consult with our board house in order to create a custom board stack-up. Not only did we need to maintain controlled impedance, but many of the high-speed nets also required matched lengths, both within differential pairs as well as pair-to-pair.
In addition to the density and high-speed signal requirements, our board design also came with complicated power requirements. Our board contains 6 different power rails, with some designed to handle 10 amps continuously. Each rail also includes control circuitry and discharge circuitry to ensure correct sequencing on power up and power down. Since we are using sensitive components, we also included reverse voltage protection, EMI filtering, ESD protection, and automatic power failure control. This power design also had to account for thermals and proper current distribution. We also made sure to minimize interference with the high-speed signals from the power circuitry. Our power design also made considerations for hardware development by including manual override controls for all rails for careful board bring-up. This feature proved useful when we were programming and testing our board before connecting the Jetson module. So this is a view of our fully fabricated and assembled PCB with the Jetson Xavier module plugged in. Not visible is the SSD located underneath the Jetson and the XTRX radios which reside on the bottom side of the board. A big complication for us was that the 699 pin connector the Jetson Xavier uses to interface with our board was out of stock everywhere. We ended up having to resort to transplanting an existing connector on one of our dev kit boards with a heavy amount of rework involved. Both we and the board assembly house had to rework the connector to even get connection on the BGA pads. To check for shorts and breaks, we painstakingly continuity tested all important pins before we tested our board firmware.
Unfortunately, the connector was just fatally damaged, and we didn't have any success with this board due to warping on the connector from all the rework. But miraculously, we were actually able to source the connector just 1 week ago. We spent the entire last week bringing up our board with a new connector. Just when we were about to give up hope, everything just started working. We were so overjoyed when we got video out of the Jetson on our custom board. We took some quick benchmarks and we observed a 1 gigabyte per second read speed on the SSD. Overall, this was the most complex board Chris and I have ever worked on. But now Zach and Griffin will detail the software side of Blue Dentist.
So to start, for the software, we'll look at this flowchart that shows how our program essentially works. ISM24 is the name of our master program that creates and controls the 4 threads of our program on the CPU and is in charge of the display. ISM24 refers to the 2.4 gigahertz band that we are watching where Bluetooth operates. First, we have the capture thread, which sets up the XTRX radio parameters such as gain, tuning frequency, and sampling rate. It then captures packets within the ISM24 band and passes those packets on to our analysis thread, which calculates the channel power and sends this information along with the packet to the noise estimation thread. In our noise estimation thread, we receive 250 samples, and we use these samples and their power levels to calculate a noise floor for each of the Bluetooth channels we are monitoring. If a packet passes the noise floor, then it is determined to be interesting, and we pass it to our decode thread. In this decode thread, we are able to find Bluetooth access codes from the received interesting packets from the noise estimation thread. If the packet we are looking at is in fact a Bluetooth packet, then we will find its access code here. I will discuss the process for finding the access code in more detail later. When we are collecting data, we are monitoring the 2.4 gigahertz band for bursts of activity. We centered our program at 2.425 gigahertz. In the waterfall plot to the right, you can see a 1 megahertz bandwidth signal that is above the noise floor. This is an example of a signal that we would decide to process and try to find an access code for. Now, the way that our Bluetooth decoding works is first we separate a captured frame into 1 megahertz channels for us to process. We then take these channelized frames and demodulate the channels to get the actual data out of the radio signal. Next, we run each signal through a frequency modulated squelch, which acts as a noise gate to suppress weak signals so that we do not waste time processing them. The resulting signal is then run through an algorithm that extracts the LAP or the access code from the signal using a code word and syndrome as a means of decoding. All these processes are done on the GPU. With the optimizations we made using CUDA, we were able to improve the run time by a factor of 10. And with these optimizations, we were able to analyze each Bluetooth channel in parallel and decode Bluetooth access codes in real time.
To present this information to the user, BlueDentist uses a command line interface program. After establishing the noise floor, the program logs each lower address part, the channel it was found on, and the file in which the data is stored. Because LAPs are static, the program can also be configured to highlight targeted devices. Now we have a quick video demo so you can see it in action.
Let's take a look at BlueDentist in action. The BlueDentist hardware is capable of running standalone for data recording or connected to an HDMI display for active monitoring. Here you can see the typical output of an extended monitoring session. The highlighted lower address parts are iPhones that we set up intentionally for testing. These have a lower address part of BB, 5B, F3, and 8D10AD. Additionally, a Bluetooth device with the LAP of 890F5E was also detected. This was not a targeted device and was simply active in the environment.
To best parallelize our hardware and software development, we made use of the Jetson Xavier development kit and XTRX PCIe connector, allowing us to closely simulate the final hardware being designed by Jeff and Chris. Throughout the software development process, we faced a number of challenges beyond just the algorithm design. One of the major roadblocks we overcame was debugging and repairing the XTRX and SOAP SDR drivers. We also used multi-threading to optimize our CPU processing and heavily parallelized channelization and decoding with CUDA on the GPU so that we could achieve live processing. The XTRX SDR also required extensive testing to properly tune parameters for noise floor estimation so that BlueDentist can be useful in any environment.
To best summarize our project, we achieved our primary goals. We completed our BlueDentist hardware, integrated the XTRX radio, NVIDIA Jetson Xavier, and STM32 microcontroller. We also developed software to scan, collect, and analyze RF data to display Bluetooth activity in real time. And perhaps most importantly, we received the commendation of our amazing sponsor. I'd like to personally thank Rory McCarthy for making this project possible with CACI's sponsorship. I'd also like to thank James Cook and Dwayne Gardner for being a huge help during the design process. We literally couldn't have done it without them. Lastly, I'd like to thank Professor Yoga, Adi, and Kyle for mentoring us throughout the Capstone Project. Thank you all. I guess we're ready for questions if you guys have any.
Please unmute yourselves. I think right now everyone is muted. If you have any questions, please unmute yourself. Okay, maybe we just move on. All right, thank you guys. Thank you, that was excellent. Thank you. All right, next, RTCM.
Is everyone here?
Yes, yes, Trenda, go ahead.
Yes, we're here. Hello, everyone. We are RTCM, Real-Time Coagulopathy Measurement, and we are sponsored by Aptitude Medical Systems, Inc. Here's our development team. I'm Justin Hemphill.
I'm Trenton Rochelle.
I'm Zamin Chi.
And we are help making the next life-saving product. So just a quick overview of what we're dealing with. Coagulopathy of trauma. It's a state someone goes into when they've suffered a traumatic injury, such as a car accident, a shooting, or a bad fall. It's a hypocoagulable state, resulting in increased bleeding or clotting, heightened resuscitation requirements, and a 4 times increased rate of mortality. It's very important to monitor this state of a person nearest to the time of injury and also monitored throughout the course of care. So there are current solutions to monitor coagulopathy, but these measurements can only be taken in a hospital or lab setting, and they can take up to an hour. This isn't great when seconds matter when treating a critically injured person. So Aptitude, our sponsor, has created a solution. They created a proprietary molecule that binds to receptors in a person's blood. The electrochemical signals produced by the molecular binding provide the coagulopathy measurement. They did this on a handheld sensor that's analogous to a blood glucose meter used by diabetics. And they've gotten the test down to about 30 seconds. A quick overview, recap of what I just said. Current solutions to measure coagulopathy can only be done in hospital lab or labs. They take up to an hour. They use stationary, often large machines, and are used by doctors and lab technicians. Aptitude solution, however, is portable, is guaranteed to be done in less than 2 minutes, is handheld, and can be used by first responders. So at the beginning of the year, Aptitude gave us their alpha prototype. It's basically just a phone, an Android phone in a case with something on the bottom, a chip, a blood chip that can be inserted. And the process here for inserting the blood is shown over here on the right. There's the chip, and you drop some blood on it. It goes through the capillaries of the chip as pictured down below. And then once the blood has gone through the chip, the measurement can be taken. So the alpha prototype was pretty remedial. So we wanted to design a new system. Some of the main product requirements of this system is that it has to be handheld and field ready during an emergency. Also, the blood within the sensor needs to be at a stable temperature for various goal temperatures. We gave Aptitude the flexibility with our final design to heat or cool anywhere between 15 and 60 degrees Celsius. This is useful for Aptitude because they are not exactly sure where the best temperature is for their test. So some of the goals of our system were to design a temperature control system. This is important because the device needs to work in any environment, in a desert or in the blistering cold. Wanted to integrate all the modules into a PCB for a small form factor, provide feature expandability, have the device charge while in use, redesign the enclosure, and of course, keep in mind that we need quick and reliable readings. Some of the design limitations imposed by Aptitude were no Bluetooth, due to the possibility of the device being used in military applications. We, of course, wanted long battery life, it to be handheld, work while charging, and work with Android. So we created a system. Here is the simplified block diagram of our system. The user uses an Android phone to control the system. The microcontroller, the slave, communicates between all of the other subsystems in our entire system. We have a blood reading system up here, a temperature control system, and of course, a power system. So we needed to choose some core modules to make this system. We started with our central processor. We chose a SAMD21 Cortex. We did this because it was low power and it did all of the communication interfaces that we needed. We actually utilized SPI, UART, USB, general purpose input and output, and PWM waveforms. Then we needed an MStat Pico. This is really a really important device for the blood reading part of our system. It's a highly compact potentiostat used for taking the electrochemical measurements and thereby providing the actual coagulopathy measurement. Our power system is pretty simple. It's just a LiPo rechargeable battery, 3.7 volts, 2500 milliamps, pretty small guy, not too thick. And we needed a battery controller to charge the LiPo safely, because if you just charge up a LiPo, it'll just catch on fire. So you need a specialized circuit, something like this down below. This battery controller also gives us some battery level readings, it boosts our output, and allows us to charge and use the battery simultaneously. Then we went on to create our temperature control system. We needed a module that could both heat and cool the blood in the blood chip. So we chose this Peltier device pictured on the right. It's basically two ceramic plates connected through PN junctions. And when given an electrical current, one plate will draw heat from the other plate. So one plate gets hot, one plate gets cold. So the coolest thing about this is that if you switch the electrical current, if you switch the direction of the current, the same side that was once getting hot will now get cold. So we can use the same side for both heating and cooling. Also, it's a pretty hungry device. It takes it runs at 9 volts at 800 milliamps. Of course, we needed to figure out what temperature we're at while we're heating or cooling up the blood chip. So we decided to mount a thin film thermistor onto the Peltier. You can see it's pretty thin by this diagram or this picture on the bottom. Then we attached a digital amplifier to it that has a 0.02 degrees Celsius resolution, which is very accurate. And we're reading the temperature about every 100 milliseconds.
Okay, so now that we have that all set up, we need to be able to control the Peltier. And we're doing this through a simple input-output. We want to be able to input the current temperature reading from the digital amplifier. And then we want to output a PWM duty cycle such that we can control the H bridge and limit the current going through the device. To do this, we're using two PID controlling objects. We're using one for heating and another for cooling because they have different tuning parameters, which I'll go over. So PID stands for proportional integral derivative, and this is a control loop mechanism that employs feedback. We are continuously calculating the error value as the difference between the desired set point YT, which in our case is the goal temperature, and the measured process variable RT, which is our current variable, our current temperature. This applies a correction based on the proportional integral and derivative terms. We look at these terms, scale them, sum them back up, and this output then goes back into the system where we then look at the current temperature again, and the error value is then calculated again. This process repeats. So PID tuning is a little precarious. So here we have an animated plot of amplitude over time. As you can see, as the PID terms, as the scaling becomes as the scaling terms become more accurate and towards the system and what it needs for a quick response, we get there in a short amount of time, it becomes stable, and we reduce oscillations. Here are our results with initial heating tests with no enclosure. When we use the scaling terms 5, 3, and 2 for the PID, we can get from 25 degrees Celsius to 37 degrees Celsius in around 20 seconds. And we also have minimal oscillations. But we then tried more testing, and when we tried the scaling parameters 7, 5, and 3, we were able to get there in around 7 to 8 seconds and we had minimal oscillations. Cooling is much more difficult, I said, for a few reasons. One of the reasons is we're working constantly against ambient temperature, and the Peltier is essentially trying to cool down the whole room, which is impossible. So what we needed to do is we created an enclosure for thermal isolation of the temperature control system. Additionally, heat from the bottom side diffuses into the colder side, which reduces efficiency, as well as a high temperature gradient reduces efficiency. The temperature gradient is the difference between the top side and the bottom side temperature. So to fix this problem, we attached heat sinks. So now we move to our enclosure design. We needed to cover the system. So we 3D printed this case, which simply lays on top with a simple adhesive, such as sticky thermal tape. And what this does is this ensures that not only is the system covered, but that the blood chip also has great point of contact with the Peltier. The goal of the enclosure is that we can simply put in the blood chip, have it have great contact, and then we have this indent here such that a thumb can go in with some blood, put in the blood, and then we have this Lego-like design such that we can then cover, cover it, shown here. This improved our heating dramatically. We were able to go from 25 degrees Celsius to 37 degrees Celsius in 4 seconds. Additionally, we were able to converge to 60 degrees Celsius in 20 seconds. Additionally, once we got to that 60 degrees Celsius, we had little oscillation. So when we put it all together, we get this giant block diagram where we have the Android phone controlling the whole system through the user. The microcontroller is connected to all the inputs and outputs, the peripherals, and getting all of their data and then controlling them. So on the top left in blue, we have blood reading system where we have our Pico connected to the blood chip. And the bottom left, we have our temperature control system where this loop is in constant, this is constantly going, where we have the Peltier going to thermistor and the digital amplifier. All of this is then controlled by the PID. And then in the bottom right, we have the power system, where we have down here a charging port, where we can also change the code to the microcontroller. This charging port then also charges the LiPo battery and the phone at the same time. And we have diode protection such that we can charge the Android phone while also the phone does not provide power back to the rest of the system.
So by realize the diagram, we have our prototype board. Our prototype board is too large and too messy to cannot fit in a handheld system. So we need our PCB design. Here is our PCB revision 1, and which is 2 layers and single-sided. It is tightly designed to minimize our area, but it doesn't come with a blood reading system. And because of the COVID virus environment, the company cannot assemble the part for us. So we need to assemble the part by ourselves. Because the part is too tiny, unfortunately, our PCB board 1 doesn't work. So we have our PCB board revision 2, which is upgraded to 4 layers and double-sided board, and also come up with a blood reading system. As you guys can see, the board is even more tight design, and it comes with the blood reading system on the top. Here is our top view of the PCB design, and it is the bottom view. Here is our finalized hardware system,
And right now, we just need a software interface to control the system. And we got our Android application. The Android application can communicate with the microprocessor while charging. And the microprocessor data can be changed in app by sending a JSON message. Here is our example JSON message. By sending this message to the microprocessor, it can change our hardware system to temperature control. So we can change the temperature by app. Here is our developer interface. The interface can change the parameters of the temperature control, such as set the go temp or changing the cooling or heating PIDs. Here is our scanning application. So this application, we can start scan by click the button and we can see the status here. We can also see the temperature by the temperature plot. And you guys can see the whole process of the app by the demo video. Here is our demo video.
We're going to take you through a demo scan of our system. We're currently in the initial state of our app, but we'll take you to our developer options where we can change the variables of the microcontroller. Here, we're changing the goal temperature, and we're setting this to 32 degrees Celsius. Here's our acknowledgement back. Now what we do is we click Start Scan. From here, we insert the blood chip. Then what we do is we insert the blood, put that onto the chip, and then we cover it. Afterwards, we click Start Scan. Here, our status information turns green, shows where we're at. Then, the current temperature approaches the goal temperature. Once the current temperature is within 0.3 degrees Celsius of the goal temperature for more than a couple seconds, this starts the M-step pico scanning process that's happening right now. Now the results are ready from the pico. We now click this button, and the results are now displayed on this screen. This data now feeds into Aptitude's coagulopathy measurement engine.
We wanted to thank our sponsors, Scott Ferguson and Radhay Patel of Aptitude Inc., as well as our great professor, Professor Sukapali, the professor and capstone chair in ECE. And then, of course, our wonderful TAs, Aditya and Kyle. And we're happy to take any questions now.
So how did you interface between your Android phone and the microcontroller? And how did you configure the host slave configuration?
To do that, we're using a USB cable, and we're splicing we're splicing the data lines and the power lines. Additionally, we have to make sure that there are resistors that are controlling essentially who is the master and who's the slave of the data. Additionally, since we're going from where the microcontroller uses a different USB interface. I think it's using USB micro P, while the phone is using USB-C. We had to make sure that those things had a correct correct translation, and essentially it's just through the resistor, making sure the resistor setup was correct, as well as the transfer between those two USB systems.
Nice. And what would you say was the most challenging part of the project?
There were a lot of parts, but one head scratcher was getting all of the. One head scratcher was not understanding what a bootloader was and plugging in our finalized PCB board and not receiving any data back. And having to do essentially a lot of Googling and figuring out how to get a bootloader flashed on a microprocessor that does not have those pins mapped out. Required a lot of tricky soldering with a microscope.
Nice, good job figuring it out.
Okay, thanks guys. So any more question, one more question, anyone? All right, let's move on then. Next.
Hi everyone, thank you for attending. We are Bermuda, a directional SDR-based local positioning system. This is our development team. I'm Crystal.
Jerry.
I'm Lillian.
I'm Leica.
Loss of GPS can result from poor signal or cyber warfare. Thus, the goal of Bermuda is to provide an alternative location tracking system to GPS. While GPS uses satellites, Bermuda is a proof of concept that a device's coordinates can be located using radio emitters and directional antennas.
So Bermuda has a couple different applications. One of them is defense, to protect against jamming during either cyber warfare or peacetime, or even potentially GPS satellite failure. Space exploration, say we want to do a long-term exploration of another planet or a moon. Scattering some radio emitters across the surface would be a lot cheaper than putting up satellites. And the Bermuda concept can be extended to vertical locating. This could allow for assisted control for activities that need 3D precision, including precision in landing, warehouse navigation, since there's no GPS indoors, and surgery with very small radio emitters and receivers.
Our system architecture is comprised of the Kerberos SDR, the Raspberry Pi 3B Plus microcontroller, the WhipMotion IMU, and 3 Autofruit radio emitters. So here we have a diagram of the system architecture. We place 3 Autofruit radio emitters at pre-designated locations external to the system. Then we have the Kerberos SDR, which is a 4-channeled software-defined radio. It has 4 antennas connected to it in order to receive signals from the radio emitters. It interfaces with the Raspberry Pi 3B Plus via USB in order to send the degree finding data to the microcontroller. The WhipMotion IMU is an inertial measurement unit, and it has a UART interface, so it uses an adapter to interface with the Raspberry Pi via USB and send it its bearing and acceleration/velocity data. The Raspberry Pi can then triangulate Bermuda's location with the data coming in from the Kerberos and the IMU. All 3 of these elements are connected to a power hub, and each of the 3 emitters has an individual battery pack.
The Kerberos SDR is our main component. As Leica mentioned, it is a coherent RTL SDR with 4 channels. Once these 4 channels are synced, it can receive the direction of signals. The direction finding capabilities of the SDR are all open source code. The data acquisition firmware performs automatic gain, sample delay, amplitude, and phase calibration at every system startup. The gain tuning procedure finds the max gain values for each of the receiver channels to use the full dynamic range of the receiver and ensure maximum sensitivity. The Kerberos SDR's frequency range is quite large, so we decided to use live signal antennas, which are omnidirectional antennas that provide a frequency range from 700 MHz to 2700 MHz, giving us enough space to choose a desired frequency for our emitters to give off signal at. We had 2 options with how we arrange the antennas, a linear array or a circular array. Although a uniform linear array, a ULA, cannot tell if the signal is coming from in front or behind the antennas, a uniform circular array causes more multipath issues and less accuracy, so we decided to go with the ULA configuration. For the Kerberos SDR, to perform direction finding, we needed to space the antennas a certain distance apart from one another, which is the interelement spacing number. So we ended up setting the antennas 0.1095 meters apart from one another which is based on our center frequency emitter. The direction of arrival estimation is calculated by the Kerberos SDR performing a time difference of arrival, TDOA, to compute the incident angle that it is receiving a signal from.
The way this works is based on a technique called beamforming, which shows how a group of low to no directivity antennas can behave like a highly directional antenna. First, we can assume that our transmitter is far enough away that we can ignore the curvature of the wave fronts as they arrive at the antennas. Now that the waves are arriving as plane waves to each antenna, you can see that the wave arrives at each antenna at different times, since the source is closer to one side of the array if it's arriving at an angle. With a sync clock and appropriate phase delays between each of the antennas, we can find the time difference of arrival of the transmitted signal to each of the antennas. From the beamforming network and the time difference of arrival, we are able to get the wavefront of the signal, and thus the direction that it came from. We chose the whip motion IMU for its accelerometer and orientation bearing readings for angular velocity and relative angle. These help us with our location method, which will be expanded upon later. In addition, the IMU has built-in Kalman filtering for its sampling. It also has a sampling rate of 10 Hz.
We chose the Raspberry Pi 3B Plus microcontroller primarily because it's compatible with the open source code of the Kerberos SDR. It runs on Raspbian, which is an Ubuntu operating system. The Raspberry Pi interfaces with the Kerberos SDR via USB, and it interfaces with the IMU, which has a UART interface with a UART to USB adapter. As well as processing the signals from the Kerberos SDR, it computes the triangulation location and plots it on an in-house built graphical user interface.
We chose to use the Adafruit Feather M0 packet radio, which has an RFM69 radio attached to it. It's powered by a micro USB, and the frequency, power, modulation, bandwidth, and data rate are all software programmable. We set up 3 emitters at differing frequencies centered around 912.5 megahertz, which is within one of the license-free ISM bands. Before we tried finding our own location, we had to do tests on the Kerberos SDR's direction finding.
Although the antennas are, in theory, omnidirectional, in order to optimize our testing and results, we tested our Kerberos' direction finding ability by quadrant to minimize any poor results due to inconsistencies in the hardware. We tested this with a single emitter at known angles at a range of distances and averaged our typical results. So the angles highlighted in gray inside the perimeter of this circle are the expected or true angles of our emitter. And the colored ones outside the perimeter are what the Kerberos estimated. So we used the green ones and the yellow ones to indicate more accurate readings, especially green, and red are the least accurate readings. Therefore, we can see that quadrants 1 and 2 tend to have the most accurate readings. And so with triangulation testing, we tried to place our 3 emitters in those quadrants because we suspect that the antennas are not perfectly omnidirectional, and these quadrants tend to be more accurate based on our findings.
Our goal was to have it such that all 3 of the emitters would be emitting at their individual specified frequencies, and have the Kerberos SDR be able to calculate each of the emitter angles simultaneously to perform quick direction finding. To do this, we had to perform frequency filtering, resulting in these specified emitter frequencies. We did not want the Kerberos SDR to be reading a huge bandwidth, as it would pick up a lot of noise and interfering signals, which would reduce the accuracy of the readings. So we opted for a 2 megahertz bandwidth. The open source code that was provided with the SDR used a real valued FIR filter. So it's a symmetric transfer function. Thus, in order to filter so that only one emitter would be read at a time, we had to space the emitters asymmetrically apart. The center frequency acts like a bandpass filter, filtering out the low and the high frequencies. Meanwhile, the low and high frequencies use a band stop filter with different cutoff frequency points. In the graph shown, you can see 2 peaks in the low and high frequency filtering. This is due to the antennas picking up the other frequency signal. However, the peak with the arrows is about 10 disciples higher than the other peak. The difference allows the Kerberos SDR to pick up the higher peak and use that signal for direction finding. To simultaneously read all 3 of the emitter frequencies at once, we had to store the data that the Kerberos SDR was receiving before it runs the DOA algorithm. This way, the 3 filtering techniques would be placed on the same set of incoming data so that the 3 DOA estimates would be from the data that comes from the same time. Additionally, to perform this filtering, we had to adjust the Kerberos SDR's FIR tap size settings. The FIR top size sets how tight the filtering is, but this comes at the expense of higher CPU usage. To counteract this, we had to adjust the decimation, as increasing the decimation would reduce computation time, making the update rate faster. Overall, it takes about 600 milliseconds to calculate the angle of each emitter. We decided to read the angle from each emitter twice before running our triangulation program against it in case there were differences in the angles. Thus, it takes roughly 2 seconds to be able to read and send the incident angles that the Kerberos SDR is storing to the triangulation program.
Now onto how we use the data to calculate our location. And actually, the Bermuda could estimate its current location using just the IMU. Problem with that, though, is that it's not very accurate due to wind and drift, which could accumulate more error the longer Bermuda is in motion. Instead, if we have some radio emitters around the area, we can use a kind of triangulation to have a much better estimate than the IMU could make. Bermuda's location tracking is dependent on radio emitters of known location and frequency across the area. And we also need to know Bermuda's starting location. Here's a simplified static example with 3 emitters. So first, we know the 3 emitter locations, so we plot them. And then for each emitter, Bermuda will calculate the angle that it's coming from. And currently we're using the uniform linear array for the antennas, which, as Crystal mentioned, means Bermuda will read the same angle both behind and in front of it. So we use the IMU to get a rough estimate of our location first. And then using the bearing, we can make an inequality to represent front versus back and test the emitter against it. The angle we've received represents the slope of a line, and the emitter location represents a point. Together they make a line, and we repeat for the other emitters. And finally, the estimated location of Bermuda is the averaged intersection of the lines. The example we just went through had emitters at a distance of 25 feet, and we got an error of about 2 feet. This other example has the emitters much closer together. The error is a much greater 12 feet, though. So the accuracy of the estimate depends on a lot. Signal multipath and angle estimation, of course, but location error won't be directly proportional to the angle error. And the closer the emitters are, the more parallel the lines can get. So the further the intersection can get pushed. For example, if the DOA happened to make the lines perfectly parallel, then the error could get thrown to infinity. Even after we calculate our location, though, there's different filtering methods that we can use to improve the accuracy. Outlier filtering in case of a straight angle reading, or we could use a moving average or a weighted moving average. Or we could use Kalman filtering, though we chose not to use Kalman filtering because it assumes data of a normal distribution, which our location estimates aren't necessarily. And also as a trade-off for faster calculation on a smaller set of data. We ended up using a combination of outlier filtering and weighted moving average. Here's an example of an unfiltered versus a filtered path. As you can see, the orange unfiltered path kind of flies off into space, and the green filtered path is more consistent.
Now we will be showing our demo video. The video shows our local positioning system, Bermuda, moving in a predefined path so that we can see the accuracy of our calculated location by plotting this on our graphical user interface.
As seen in the demo video, we have built a GUI that looks like this to visualize the path that Bermuda has traveled. Since it's currently proof of concept, we can see all the calculated estimations against the expected path in order to compare and gauge our accuracy. We can see the expected points and path in green and all of the calculated estimations by Bermuda as it travels in the blue triangles. Each of the expected green points has several corresponding blue estimations because we briefly pause at each of the pre-designated points in order to improve the accuracy. Among each set of estimated points, the increase in opacity represents recency. Along this particular 3-foot path that Bermuda takes, the error ranges from a couple inches to approximately half a foot. We expect this error to reduce with better hardware and generally better conditions.
Lastly, we wanted to thank and give a big shout out to our sponsor and all of our mentors for their guidance and assistance throughout our project. Thank you for all of your attention. We will now be open to any questions.
So I wanted to ask you, you said that the code for the KerberOS was open source. So did you have to make any significant changes to your code, to the code?
Yeah, so it was open source, but most of the changes that we had to make for the KerberOS code dealt with the filtering. So we had to make sure that we were able to read all 3 of the emitters simultaneously, but we did not have to deal with adjusting the DOA algorithm part of the code.
What's the maximum range of your guys' system?
So do you mean the range that our antennas can emit at, or the range that we're dealing with the emitters?
I guess both. The range at which you would be able to get within a certain error from like the actual location. You know, you guys can actually read the data.
So in the video that we showed, because I had to do it in my backyard, I was only able to get within a 5-foot radius from the emitters to the antennas. So then because of that, it was difficult to be able to move the system to go far and be able to track that location. But before, we were able to get at about a 25-foot range. So then since we were able to get at a 25-foot range, it would have been quite a lot larger to be able to move the system. But that's in terms of, yeah, that would be in terms of the distance.
What would be the challenges with scaling it? Is it just a bigger transmitter antenna system, or what were your limitations on that size?
Oh, well, one of the limitations is that like each emitter that we use has its own like range depending on the power level that we use. But if we were to expand our project, we could also implement like support for more emitters, so that if you could spread the emitters out over a larger area, then the Kerberos would be able to be in range of 3 emitters no matter where it moves.
Yeah, Alan, also one of the extended goals of the project was to use the cell tower signals to localize. So you can actually use the cell tower signals as emitters also. So that would obviously increase the range quite a bit.
Another thing we could have improved on was we wanted to use a better processor, but we couldn't because of logistical reasons.
Thank you.
Okay, thanks guys. Let's move on to the next presentation. WizHawk.
Having some lag at the moment. We're going to give it a second until it gets screen control. There we go. Good morning, ladies and gentlemen. Welcome to the presentation of WizHawk RF Silent Drone Navigation. I'm Matthew Dupree, the student team lead, and I'm here with...
Hi, I'm Shihan Liu. I'm responsible for data analysis.
Hi, I'm In Chao. I worked on printed circuit board design.
And the project roles got a little more mixed up than that. We were all working on different parts of the project all together at different stages. So first, an overview. What exactly am I talking about when I say RF silent and drone navigation, that kind of thing? The basic goals of the project are we want to lift off from a boat that is underway at sea, or not underway, we just want to lift off from a boat at sea, land on another boat at sea. And that is a very tricky challenge because landing on a boat at sea means we have a limited size landing area. We have a moving landing area because the tides and the waves are going to push the boat around. And if we miss that landing area, our hardware ends up in the water, and wet hardware is usually non-functional hardware. We also want our project to be RF silent. That is, no radio communication. There's no way to locate the drone in space because there's no pilot with a remote control maneuvering it. There is no landing beacon that's going to tell the drone exactly where the deck of the ship is. And there's no external processing to send the video footage out to say, okay, yeah, the ship is there. Everything we do has to be on board the drone, which means we need to identify the landing target via some kind of computer vision on the energy budget of what the drone's hardware can handle. Just to formalize that problem a little bit more, we've got 2 boats, a lot of water between them, and a drone that needs to lift off from one ship and land on another. We also want to do that without talking to anybody. We can't have a pilot on the ship. We can't have a pilot in Nevada. We can't have a landing beacon that would mark out the location of the ship. What we need is something entirely visual that's hard for other computers to pick up that we can use to identify the ship we want to land on. And so we've focused on the latter half of this problem, trying to get the drone down onto a target ship's deck without communicating with that ship and without communicating with the outside world. And so we've assumed that until we can get within being able to see the ship's deck, we can use GPS to navigate to a location we expect the boat to be. Here's the block diagram of our project, and Ying Chao is going to break it down a bit more.
I will introduce these blocks in details. There are 2 processors in our system. The main processor is Raspberry Pi, which handles the computer vision part. A Pi camera is connected in parallel with the Raspberry Pi in order to detect the tag. There used to be a servo attached to the camera, which allows us to get up to 180 degrees of view, but we had trouble with vision transformation. With a moving servo, we need to configure different sets of parameters at different angles. So we decided to use only a fixed down-facing camera for detection, and that's enough for searching the tag when the drone is up in the air. To control the Raspberry Pi, we SSH log into the system using our own computers and type in the launch command. The co-processor is PixHawk, which interfaces with the Raspberry Pi using UART transmitter and the receiver. It ensures drone stability in flight. Motors make the propeller spin. Here we are using 3-phase motors. Comparing with single-phase motors, 3-phase motors are more commonly used in industry, since their power is over 150% greater than that of a single-phase motor, and less noisy. Finally, all the black arrows here represent the power flow. A 4S LiPo battery is the only power source. It supplies the flight controller and the motors. The Raspberry Pi can only support 5-volt input voltage, so a voltage regulator is needed to convert the high voltage to 5 volts to supply the Pi.
Next, we're going to break down the hardware layout on the chassis. Shihan?
Yes, so we will introduce our design layer by layer. On the top of the drone, we have GPS, flight controller, and telemetry radio. In the middle part, we have a companion computer and a mounted camera. At the bottom, we have a 4S LiPo battery. For the flight controller, we choose to use PixHawk 2.4.8 because it comes with a GPS antenna and supported by Audicopter APM firmware, which contains precision landing mode that is what we needed for landing detection. And we included an anti-vibration pad stick it under the flight controller to ensure stable flight. We also mounted a GPS block for achieving drone's longitude and latitude data without RF communication. This module will not be used after a landing target detected. The telemetry radio is mounted on one of the 4 branches for balancing. It is used for broadcasting information and displaying in ground control station during our flying experiments, and we can take this part off in the real flight.
The middle layer consists of a companion computer and a camera. The component we chose for the companion computer is Raspberry Pi 3B+. It's the final revision in the Raspberry Pi 3 range. Comparing with other models in 3 range, it has faster Ethernet. We can log into the Pi when we are on the same network. Its job is to perform computer vision tasks to identify the target and communicate target transform to the flight controller unit. Then here is the bottom view of our drone. We mounted the camera on a 3D printed board. It's Raspberry Pi camera module V2. It's capable of taking photographs of high resolution. We use this to detect April text in a lower resolution because we want to get higher frame rate. But due to Raspberry Pi processing limitation, it can only process about 10 frames per second. So that's what 10 FPS here means. At bottom, there is a 4S LiPo battery. It's the only power source for our whole system.
Okay, and now we're going to talk a bit about the printed circuit board that we use to regulate power going to the Raspberry Pi.
This is the schematic of our PCB. It functions as a voltage regulator to convert the input voltage from 14 to 22 volts to 5 volt output voltage. We also put a diode after the input voltage in order to prevent reverse current. Because during testing, when we powered the Raspberry Pi by USB, we noticed that the peak socket was also lighted up. So a diode can prevent this from happening. On the left, this is the PCB board design made with Eagle software. Then we have the final product of our 2-layer PCB. It's 45 by 59 millimeter large. The inductor and the diode occupy most of the space. We also put a lot of drill holes for thermal dissipation.
And now I'm going to break down the software stack that we use to make the drone fly to the areas we wanted to go to. First, and most critically, is the system we use to identify the landing location. We're using the April Tag 3 visual fiducial developed by the University of Michigan. The tag is represented by a whole bunch of little bits, the white and black squares you can see. And so there is a wide space of tags that one can generate, and only the target tag is going to be detected by the April Tag 3 library. So the system has an extremely low false positive rate. It locates rectangles in the environment. It reduces down the code by a Hamming scheme compressions algorithm, error correction algorithm, sorry, and then determines whether that code is the specific tag we're looking for. And using all of these stages in hours and hours of testing, we've only had about 32 misdetected tags, and every one of those tags had a different ID from the one we were intending to land on at the time, meaning they did not affect our system whatsoever. With the current onboard processing of the Raspberry Pi, we are able to read in a 640 by 480 resolution, which at a 5-meter altitude gives us a 5-meter deep by 6.7-meter wide box below the vehicle, in which we are searching for this 16.5 centimeter square tag. If we had more processing power, we could read higher resolutions and get significantly better ability to recognize the tag at distance, higher search altitudes. At the moment, though, the highest search altitude we're able to detect the tag at is 7.2 meters. Next, the flight control unit on board the craft also needs a piece of software telling it how to keep the drone stable. Our first choice was the PX4 autopilot, which is a beginner-friendly OS with lots of useful debugging features, such as the Mavlink shell that lets us run debugging commands on the Pixhawk itself over the Mavlink standard, so from the Raspberry Pi. However, Pixhawk would only accept coordinate frames in what's called local northeast down, meaning a frame defined when the drone takes off, where X is north, east is Y, and down is Z. And unfortunately, we're trying to lift off from a moving boat and land on a moving boat. So that local northeast down frame doesn't work for our use case because the landing target will be moving around. And so we had to move to a different OS. Second, we chose Arducopter multicopter autopilot from the ArduPilot series of autopilots. This is much more heavily used in industry, has many more advanced features and configurations, but it is slightly older, and its code base is basically spaghetti. There's all sorts of dependencies every which way. It's also missing useful debugging tools like the Mavlink shell, and we ended up having to use a post-hoc debugging process I'll go into in a moment. The companion OS, that is the OS on the companion computer, our Raspberry Pi 3B+, is Ubiquity Robotics' Ubuntu Mate 18.04 with ROS Kinetic. Ubiquity Robotics is providing this distro of Ubuntu free of charge with open source, and so there's no legal liabilities relating to it. ROS, the robot operating system, is an inter-process communication scheme, allowing us to spread the processing of our vision information across all the cores of the Raspberry Pi to get the maximum use out of the Raspberry Pi hardware. It also has a number of logging tools so that we can read the inter-process communication messages and analyze the behavior of the drone after a flight. This is the processing pipeline we built inside of ROS, and I'll break it down. First, we read the Raspberry Pi images from the Raspberry Pi camera using RaspBiCam node. This node initially published images in a way that was unsynchronized with the camera info state, and we had to rewrite a large portion of the node to produce the images in an unencoded format AprilTag ROS would accept, and with the synchronization information, the camera state information arriving synchronized. AprilTag ROS is a wrapper around the AprilTag 3 library that extracts the location of the tag relative to the camera. It then produces those tag positions which travel to Vision to Mavros. Vision to Mavros is a small wrapper package that just translates the vision tags from the space of I'm the camera, here is the tag, to this is the tag, this is the origin of our space, the drone is here. And we send those targeting positions of the drone to Mavros, which is a wrapper for the Mavlink communication standard. Mavlink is sent over UART to communicate with the Pixhawk, and it is a common autonomous drone component communication system. And then Mavros sends the data to the flight control unit. At every stage in this process, we pulled out logging data that we reformatted for vsub.py, a custom visualizer we made to make sure that all of the transformations were going correctly because we had a number of issues along the way. But with the switch to ArduPilot OS, we no longer had the Mavlink shell on board the vehicle, and so we ended up having to read the logs in a post-hoc manner using MavExplorer because we could only get data flash logs after a flight or a test. Now Shihan will talk a little bit about more about the transformations and debugging tools and all of that process.
So right now we are focusing on extracting location data of the drone relative to the camera position. For the ROS operating system, there are several command line tools. ROS topic echo is one of them. We use this tool to listen to the topic TF, which is subscribed by Vision to Mavros node. And this node would help convert angle and distance according to east-north-up conversion with user input rho, pitch, yaw, and gamma angles. We do one more transformation into a northeast down frame, which is used by our flight controller. After the flight controller gets the data, we use the Mavlink share, which is used for running commands and displays the output. We at this point could able to see what the message contents received for Pixhawk. Simply displaying the position data is not enough to compare the consistency information between our companion computer and flight controller. So we convert the Mavlink output and write into a YAML document stream. Meanwhile, we grabbed the display data source from Vision Post from the ROS node and transferred to local computer as sources for our VSubPy debug program via SSH pipeline. With these two sources, we could better visualize them onto a Matplotlib 3D plot for more straightforward understanding.
Thank you. So all that was a little complicated. Let's just see it in action. Here we've got a demo video of the craft doing a flight. And I'm not seeing the interface for playing it. Kyle? Oh, shucks, there it was. So our mission is to take off at node T and land at, and we lost the slide. The mission is taking off at node T and landing at node L. The red trajectory on the map is caused by tracking of the tag and pursuing the tag, which we were dragging back past the takeoff location, meaning it was tracking a moving tag on the ground that happened to pass through the region it was expecting to land in. I'll stop moving the mouse so you can start the video and we'll just run straight through. Sorry, Kyle. Spool up. Spool up is when we're getting the motor started, because unless all four are running, the vehicle will flip over. Auto mode is automatically determining the GPS coordinates to travel to and just following a pre-programmed mission. It will go to a 5-meter hover and then wait there for 3 seconds. I start moving the tag when it reaches that hover. It then enters landing mode and is now pursuing to catch up with the tag. Here, it slightly overshoots the actual location of the tag and corrects its positioning, and then continues its descent. Only in the last quarter meter does it lose sight of the tag. It loses sight of the tag because the tag at that height versus the vehicle is such that the entire camera field of view is taken up by the tag. And unless the camera can see the whole tag, it will not register the tag and make any detections. This project has had a lot of challenges along the way, and we'd like to extend our special thanks to NAVSEA for funding our project research, Alan Yeager for being our contact with NAVSEA, Dr. Yogande Iskupali for running the UCSB Computer Engineering Capstone this year, Aditya and Kyle, our 2 TAs, for helping us so much in office hours, and Qualcomm, NAVSEA, and UC Santa Barbara Engineering all together for funding the Capstone program. We'd also like to thank all of you for listening. Anyone have any questions?
How many times did you guys crash your drone?
We had at least 8, 10 flight attempts that ended with a harder than expected landing.
Hey guys, good job. Knowing what you know now, what would you have done differently if you were starting over again?
Start with the APM firmware, pick a flight controller that integrated with the ESCs directly. So putting the ESCs on would have been easier. And then, I mean, honestly, there's so many little details in the whole process that it's difficult to go over everything we could have changed. Yingqiao, Shihan, any other specific ideas? A lot of our problems in the project came from just not knowing certain configuration options existed and them being in a state that wasn't conducive to our vehicle operating in this manner. All sorts of rotation transformations and parts of the Kalman filtering. The vehicle itself, the reason we needed the spool up extended is our motors take a moment longer to start up than we realize. And so some of our crashes were related to it not starting those motors correctly. On top of that, there were motor spin direction configurations that we had to deal with, and that delayed almost our entire first quarter. It's just so many bumps and things to learn along the way. And if we started over now, we could definitely make all the progress we've made in a quarter.
Well,
that's
challenging
because
problem.
we made all that progress. Yeah.
Yeah, it's a challenging problem. A lot of people are trying to solve in a lot of different elements. So good job. Hope you guys learned something, had a little bit of fun along the way.
Thanks, Alan.
Okay, thank you, Matthew. Thanks, Shihan and Incha. Let's go on with the next one, Guardian.
Good afternoon, everyone. So we are the Guardian, and sorry, there is some delay for the PowerPoint. Here is our development team, and I'm Wei Yun.
I'm Lexus. I'm Jiajun.
I'm Ning.
We aim to use the autonomous drone system to solve the elephant-human conflict. And this kind of conflict is very prevalent in the worldwide because nearly 20% of the human population live in or near the elephant habitat. And over the 100 years, the number of African elephants decreased for more than 90%. And the cooperating is one of the major forms of the conflict. According to the WWF, World Wildlife Fund, about 65% of the crop destroyed are wheat and 21% of the crops destroyed are sugar canes. And these two kinds of crops are the major source of income for small plantations. Up to 600 pounds of food can be eaten by a single elephant per night. And this means a lot to a small household. And that also causes a lot of damage to large plantations because, for example, in Riau, the largest oil producing province in Indonesia, about $100 million are lost by cooperating each year. And in India, according to the national report, up to 300 humans and 50 elephants are killed during cooperating each year. And according to the National Geographic Channel, the elephant range, about 500 people are killed by elephant each year in the world. And this photo is taken in Riau, the largest oil producing province in Indonesia. You can see in the photo that the elephants are destroying the crops and wasting millions of dollars.
So this is the basic flowchart of our solution for the elephant-human conflict. Basically, we utilize the fact that the elephant is afraid of drone noises and it can be used to scare them away. And so the first step, we'll try to place a GPS tag on the elephant by tranquilizing it. We will then probably put a bracelet on the elephant's ankle, or maybe we'll just strap a GPS tag onto the elephant's neck. And then a ground base is set up in the place where the protection of the crops are needed. The ground base will emit signals which the GPS tag will be able to pick up when a signal is strong enough. So the range of the signal from the ground base basically defines the perimeter of the protected area we want to prevent elephants from entering. And the next step will be when the elephant with a GPS tag going to the range of the signal of the ground base. So when the signal is strong enough, the GPX is woken up from sleep mode and start to send out real-time GPS coordinates. And the third step is when the drone receives these coordinates and fly to the coordinate of the elephant. And next step will be when the drone is about to reach the elephant coordinate, the onboard camera is turned on and the footage is then analyzed with AI algorithm loaded on NVIDIA Jetson Nano to identify and track the elephants effectively. The final step is since the elephant's afraid of drone noises, they will be able to chase the elephant away from the ground base and effectively prevent the elephant from damaging the crops. And okay, so this is a visualization of the process we proposed. The yellow shaded circle represents a region of the signal covered by the ground station. And, the ground station is represented by the three little houses in the middle of the circle. So the yellow shaded circle is the region where the signal from the station will trigger and wake up the GPS tag on the elephant. So as you can see right now, the elephant is outside the yellow region, which is the protected region we want to prevent elephants from entering. And right now, since the elephant is outside of this region, the drone is still on the ground. And when the elephant comes into the protected region, around the ground base, the XP module receives signal from the ground base, which triggers and wake up the GPS tag on the elephant. And then the GPS coordinates of the elephant is sent out by the XP module on the GPS tag and is then received by the XP module on the drone. The drone will then take off. And the drone will then use waypoint navigation to fly to the coordinate of the elephant and try to scare away the elephant. And when the drone is close enough to the position of the elephant, the onboard camera will turn on. And finally, the onboard Jetson Nano, which is running the AI algorithm, will try to pinpoint and track the elephant's movement using the footage captured by the camera. And this will ensure the drone is chasing away the elephant in the right direction. And then the drone will try to maneuver until the elephants are outside the protected area.
So this is the system block diagram of our whole design. The drone comes with two main parts, the onboard computer Jetson Nano and the DJI-N3 flight controller. The Jetson Nano runs the object detection and tracking program with the camera connected, and it sends the flight control commands through UART to USB connection to the N3 flight controller. The flight controller then sends signal to the motors to control the drone. A power system is providing power for both of them. There are 3 XP modules, one in the ground base, one on the drone, and one on the GPS tag. A battery provides the power for the microcontroller to control the GPS module.
So right now I'm going to walk you through the schematic of our GPS tag. On the left-hand side here, you can see a sketch for our schematic in the Eagle. And on the top right here, it's a high-level block diagram for our GPS tag. And over here, we have the Arduino microcontroller. And this corresponds to the XP module that is responsible for the communication, sending out the GPS signals. And this one is the GPS module that's responsible for locating the elephants. The SD card here is used to store the coordinates of the elephants for future research. And this is our PCB layout. So we use the 4-layer board, and the size of this PCB is very small, and it's also very light. So if we install the GPS tag on the elephant will not notice it. And according to our estimation, the GPS tag can last for about 200 days. And it's calculated based on the storage of our battery and the power consumption of our components. And in fact, we use two kind of power system for our GPS tag. One is the backup battery for the GPS module, and then we also use a LiPo battery to power the whole system. Here is our assembled PCB for the GPS tag, and you can see it features the SD card, the GPS, the ZigBee, and the Arduino microcontroller.
So for the drone part, we use Terra 680 Pro frame that comes with the motors and ESC, electronic speed control. Jetson Nano is the onboard processor to run the object detection and tracking autopilot program. DJI-N3 flight controller controls the drone to perform flight actions. And we use a camera for object detection and tracking, and AXB to receive the GPS location from the GPS tag. And the 6S battery provides a 20 minutes of flight time and a range of 4 miles.
Okay, so we use Jetson Nano as our onboard processor on the drone. We choose this for computer vision since it has a decent NVIDIA GPU, which is great to speed up the neural network detector we're using. It also has a low power consumption, so we can extend battery life for our drone. However, turns out Nano is still really constrained in terms of compute. So it's still challenging to get our tracking algorithm to run in real time on this hardware. So we combine neural network with a lot of the other efficient techniques to get it to work. And I'll come back to that later.
So we choose DJI-N3 as our flight controller, mainly because of its stability. It has 2 IMUs providing dual IMU redundancy, making the drone much less likely to fail to operate and crash. It comes with a GNSS compass and onboard GPS to give us the direction and GPS location of the drone. A built-in power management unit, PMU, provides the power supply. The end pins are used to control the motors, an API port with the UART connection to receive the instructions from the Jetson Nano. And the DJI onboard SDK are used to speed up the programming part. The DJI onboard SDK is installed in Jetson Nano, and it is the interface for DJI-N3, providing functionalities such as flight actions and aircraft state data retrieval. For example, it can make monitor landing and takeoff, perform roll your pitch to adjust the attitude, get data like direction, GPS, and altitude. These are essential for developing the autopilot program to herd the elephants away.
Okay, now I'm going to break down our software stack. So our software architecture is split into 2 parts, visual tracking and drone control. Tracking is written in Python to work with a lot of the machine learning libraries, and our control is written in C++ so that we can use DJI SDK and be flexible in low-level interfacing. When we launch our control program, it will spawn the tracking program as a separate process and communicate with this through a socket. The tracking program will send the bounding box around the elephant to the control program at each frame. And then the control program will run PID control on the bounding boxes. The control algorithm uses the area and the centroid of the bounding box to control the drone. Okay, and that brings me to how our tracking algorithm works. Common filter is a great algorithm to model the motion of objects, so we use that to keep the tracking smooth. Bounding box position and velocity encoded in the state of the Kalman filter. Optical flow takes 2 frames, an old frame and new frame. After it matches the object from the old frame, it will output a new set of tracks. And these tracks are used as a measurement to update Kalman filter. Kalman filter will then output a new state, which has all the bounding box information for the new frame. We also run a CNN detector every 5 frames to detect new elephants. So the detector takes the current frame, outputs a bunch of detections, and we associate each elephant detection to each track in the old frame. If we associate detection to a track with high certainty, we can just keep tracking it. But if we can associate detection, we'll just create a new track for that object. And again, we use the final output tracks to update command filter. Because we will only run the detector every 5 frames, so we can actually get everything to run at 32 frames on average, which is already in real time. That's pretty nice. So how do we actually transfer the bounding boxes into our control signal, to the drone? As you can see, the green box in the image is the bounding box output by our visual tracking. It's basically the feedback signal we use for control. The blue box is our reference bounding box, which means we want the green box to be as close to it as possible. The red arrows are the control arrows. The arrow in the middle, delta X and delta Y, shows the difference between the centroid of the green box and the centroid of the entire video frame. The arrows at the 4 corners, delta A, shows the difference between the area of the green box and the blue box. We pretty much fix the throttle of the drone to keep it at the same height. We use delta X, the horizontal difference, to control the yaw and roll of the drone. We use delta Y, the vertical difference, to control the pitch. Delta A also controls the pitch since it roughly reflects the distance to the elephant. So we want to move the drone forward or backward based on that.
Okay, so this is our demo video this is a simulation. So we didn't include anything related to GPS waypoint navigation because it is basically a building function of the DJI SDK. So basically we are simulating the tracking movement of the drone. The position of the elephant is approximated by the center of the rectangular box generated by the AI algorithm, which is what Alexis talked about. So in the simulation, we basically have the drone moving in the same direction as the elephant in the footage. And as you can see, there's a coordinate system in the middle of the screen, and it's showing the drone flying past in the simulation. Okay, so let's play the video. So the first clip basically shows the animal moving towards the upper right. And as you can see, the drone is basically replicating that movement in this simulation, essentially tracking the elephant. And the second clip is the elephant moving towards the right, and the drone is also moving towards the right to track it. And the last clip will be basically the same thing, the only difference being that the elephant is now moving towards the left.
So we would like to thank Professor Yoga and Professor Schultz, Dee and Kyle for their very insightful technical discussions. And that's it for our presentation. Any questions?
So based on your experience with this project, would you make any changes when deploying this in like actual regions that have elephant-human conflict?
There are some like actual like projects that's already like deployed in Africa. So very similar to ours, but I think our like, a combination of like GPS and, visual tracking system will like do this job more effective than those like existing systems. So they are already applied in some sense.
And we do think that our project can scale. We can like improve our project to make multiple drones coordinate at the same time to like herding like a larger area for elephants to herd them away.
So was drones the ultimate solution to this problem? Did you guys also consider networks, sensor networks, like a mesh network of deployed sensors or speakers? And why did you then settle on using drones instead?
One problem with the installed speakers is that sometimes if you deploy it in Africa or in some remote places, they will be stolen easily. So if you use drone in the air, no one can steal it.
Okay, thank you, Vijay. Thanks, guys. Let's go on to the next presentation.
Hello everyone, my name is Ini Wang. We are Team C Star, and I'm responsible for automation, data analysis, and video processing.
I'm Ranmo. I'm responsible for design, video processing, and testing. The purpose of our project is to help Professor Oakley in marine science to study some marine species called ostracods. They are like very small shrimps, and they are interesting because they can generate beautiful light when they move or communicate with each other. Besides, ostracods have large diversity and their evolution is very fast. So study of ostracods is greatly valuable in marine science. Our project C-Star is based on a previous ECE project, WALL-E, which is made for Oakley's lab as well. We need to record both videos of the bioluminescence from ostracods and the light levels of the bioluminescence with extreme precision. After that, we need to post-process and analyze the videos to get the data for further study. The previous team had finished the first part, and their equipment has 2 Vortex cameras, which can record the videos underwater. So our work focuses on the following 2 aims. Now, there is no such existed device for this specific purpose, so we must design it with basic elements.
And our solution is to use PMT to record overall light levels. After we collect data from water cameras, we will pause the process and analyze the recorded videos in the following order. We will start with denoising, RGB conversion, ostracods detection, temporal signal identification, 3D coordinate extraction, stereo calibration, frame matching, and stereo rectification.
This is the block diagram of C-Star. We added the PMT and the lattice-panel computer beside the original WALL-E device. Both the scene of the water cameras and the screen of the lattice-panel computer can be shown on a waterproof monitor, so it is easy to operate underwater. This is the PMT we use to record light levels. It is an extremely sensitive detector of light that it can count the number of photons that enter in its round window. It is essential for studying ostracods because the light level change can accurately tell the researchers the activities of ostracods. We chose this type because it's high quality, small size, and USB interface. So we can use the single board computer to supply its power and control it. For running the software controlling the PMT, we use the lattice-panel single board computer. We chose it because it has Windows 10 operating system, which is required by the PMT software, and its size is small, about 7 centimeters by 8 centimeters. Besides, it only needs 5 volt at 2 amp power supply, so we can use normal battery as power supply underwater.
We used the software called Hamamatsu to control the PMT. As you can see in the screenshot, users have to input the gate time and gate number and search the device manually. However, it's impossible to do that when PMT is in a waterproof casing underwater. So we wrote a script to control the software and have it complete the process automatically after users preset the configurations. And here is the result of PMT, and it shows how many photons passed through the PMT every 10 milliseconds. So when there is an increase of number of photons, it means obstacles flashed.
As we mentioned before, our PMT needs to work underwater, so we designed and made a transparent waterproof casing. It is made by 2 centimeters thick acrylic material, so it can also work under great water pressure. Then we designed the casing peripherals for fixing the Latipenda computer and the PMT in the casing. These are the models of the peripherals for 3D printing. Although we didn't get a chance to print them out due to the coronavirus, it's easy for Professor Oakley to print them out in his lab later. Besides the PMT automation, we have some jobs to do for the videos recorded by the water cameras in Wally. The bioluminescence from obstacles is wonderful like this image, but our cameras cannot take the scene like this. The reality is like this image. The frames of videos are very noisy, and the white point like the circular one is the light from obstacles. Therefore, we have to finish the video post-processing before further analysis. The first step is denoising. We roughly denoise the video by judging the grayscale value and eliminate most noises at the beginning, so we can get the resulted video like the right one. However, this is not enough because some noises have relatively high brightness, like the one shown in this example. So we still need to denoise the video by looking at other criteria. Therefore, we judge the size and the duration of the light and the max brightness and brightness change of a small part of the video in one time period. In this way, we can eliminate all noises and keep only the real signals.
In order to restore the signals, after denoising, we converted the signals from grayscale to RGB. And this is part of the video after denoising and RGB conversion. As you can see in the video, the signal occurred a few times. And our program can find all the signals occurred in the video and take a screenshot of each signal's brightest frame. All the frames will be saved to local for future analysis, and return a graph to show the relationship between the light levels and time. Also, the program will find signals XY coordinates and then calculate the 3D coordinates correspondingly. With the 3D coordinates, it's possible to visualize obstacles movements. Also, because we are using fisheye cameras, so the objects and the signals are distorted in the videos. Therefore, after we finish the 3D coordinates extraction, we need to do the stereo calibration. We first calibrate the checkerboard and generate the map and apply the map to the video. Then, because of the system errors, the left and right cameras will now start recording at the same time. Therefore, the two videos frames are unmatched. In order to match the frames, based on checkerboard movements, we find a turning point of the checkerboard in each video and then cut the videos. For example, if the left video is 12 frames ahead of the right video, we will cut 12 frames at the beginning of the left video and cut 12 frames at the end of the right video. In this way, two videos will be frame matched and have the same length.
And last, we did stereo rectification to the two videos. This step crops the two videos so that the signals in the left and right videos have the same y-axis. In this way, the analysis for the coordinates will become much simpler. After this, we can get the final resulted videos. The following is our demo video. This demo video shows the functions of our video post-processing. The first step is denoising. And the result is clear, so we often use this result in analysis. This is RGB conversion. This step is mostly for demo the real color of ultracodes, and it is better to apply this for videos containing multiple ultracodes. So the ultracodes will become more clear and colorful. Then this is the stereo calibration. You can see that the lines of the chessboard are straighter in the result. Finally, we use frame matching and stereo rectification to make the left and right video have same time and y-axis offset. Through the whole project, we've finished much work for both the PMT and the videos. We first add the PMT part on the device for studying ultracodes, including PMT automation and casing design. Then we completed a set of video post-processing like denoising, RGB conversion, stereo calibration, frame matching, and stereo rectification. We also did some analysis for the videos, like detecting the ultracodes and calculating the 3D coordinates of the ultracodes.
At the end, we want to thank Oakley Lab and Professor Iskafli, Kyle and Adi for their help and support throughout the whole year. Thank you very much, and we are open to questions.
So if you had some more time to work on this project, is there any more features you would have liked to implement?
Sure, because there are different kinds of ultracodes. So if we have more time, we'd like to do like related to machine learning to detect which kind of ultracode it is. Okay.
Okay, thanks guys. Let's go on to the next Intelli site.
Hello, everyone. We are IntelliSpy, and our project is Environment Awareness for Low Vision Patients. The IntelliSpy team is made up of Rafael, who is in charge of the camera software integration, myself, Vanessa Mejia, and I was in charge of the PCB and mount design, and Xinwan, who was in charge of the IMU software integration. When we are out in the world, we are able to understand our surroundings by using both our global and local context. Our global context refers to where we are in the world, things such as what street we're on or what city we're in. Our local context refers to what objects are in our surrounding environment, things such as how many cars or people are directly in front of us.
According to the World Health Organization, there are 285 million people, low vision individuals in the world. Many of these individuals face many disadvantages when acclimating to the environment around them. Although technology has helped them understand their global context, things such as where they are in the world, like I mentioned before, using GPS, they still have to rely heavily on their senses and on the people around them in order to understand their local context. Technology is still unable to help them understand what is in their surroundings in a quick and easy way. The solution. IntelliSight solves this problem by developing a pair of smart sunglasses that uses visual information from a camera, orientation information from an IMU, and location information using the phone's GPS. This is all combined and is able to relay an in-depth understanding of the user's surrounding. This information is sent over to the user's phone, and once on the user's phone, our application combines this information and uses computer vision as well as maps information in order to identify the buildings and the objects directly around the user. For example, if the user is standing on the left-hand side of this image, our system is able to relay back to the user that they are standing directly in front of the UPS store. Moving on to hardware. Here we have our block diagram, which shows how everything works together. We start off with our LiPo battery, which powers our PCB, and our power boost takes the 3.7 volts from this battery and is able to output 5 volts in order to power our camera. Our camera is connected to our microcontroller using SPI, and our IMU sensor is connected using I2C. Our microcontroller is able to gather both the information from the camera and the IMU sensor and send it over to the phone using Bluetooth. On the phone, we are able to process this information using our application and then send the relevant information back to the user's headphones using Bluetooth as well. When we were designing this project, we knew that we wanted it to be hands-free, which is why we decided to use the ESP32 as our microcontroller, due to the fact that it has integrated Wi-Fi and Bluetooth modules. The ESP32 interfaces our camera and our IMU sensor. It takes this data and sends it over to the phone using Bluetooth, and it also has an onboard USB to serial converter. The operating voltage for our ESP32 is 3.7 volts. For data collection, we use both an IMU and a camera. The inertial measurement unit we decided to use was the BNO055. This device collects the user's orientation data and is also able to capture the user's gestures, things such as a head nod. The operating voltage for this device is 3.3 volts, and it is interfaced to our ESP32 using I2C. The camera we chose was the Articam Mini 2MP, and we use this when the user wants to know what is in their surrounding environment. They're able to snap a quick picture with our camera. The operating voltage for this device is 5 volts, and it is interfaced with our ESP32 using SPI. For power supply, we had a LiPo battery, which has an operating voltage of 3.7 volts, and this is what powers the PCB. We also have a Power Boost 500C, and this takes the 3.7 volts as an input and is able to output 5 volts in order to power our camera. Moving on to our printed circuit board. This is our PCB schematic, and we have our power boost, our microcontroller, our IMU, and our camera header pins all on our PCB. This is our PCB layout. We wanted to keep it as small as possible in order for it to fit nicely on the user's sunglasses. And so this is why it is 2.67 inches in length and 1.15 inches in width. And it is made up of 4 layers. This is a picture of our final PCB. Moving on to software. For software, we have two different modes. We have the first mode, which is camera mode, and this has object detection. Mode is our IMU mode, which has gesture and building detection, and it also has text-to-speech. Moving on to camera mode. In camera mode, the users are able to take pictures of their surrounding environment when they want to know what objects are directly near them. Our camera is able to send this picture to our ESP32 using SPI, and then from our ESP32 to our phone using Bluetooth. Once we are on our phone, our application is able to identify the objects in the pictures using TensorFlow Lite, and then we relay the relevant information back to the user using text-to-speech. The users are now able to have a good understanding of what objects are in their surrounding environment. Moving on to IMU mode, I'll let Xinhuang take it away.
Hi everyone, I'm Jinyuan, and I will give you guys more detail about our IMU mode and also our final product. And first, let's look at what happened for our IMU mode. So here is a picture, and first of all, here is the IMU sensor like we used to detect user's gesture, and it's set on the side of our sunglasses, so it's easy to capture the motion for user's head. And then once we detect the desired gesture, it will switch to collect bearing data, and then the data will sent to the microcontroller, and the microcontroller will transmit the bearing data to our app via the Bluetooth attached on the microcontroller. And then as our app receives the bearing data, and also based on the user's GPS location, it will start to scan along the bearing to detect the landmark. And finally, the results will return in voice. Next, let's talk about what happened on nodding. And let's look at this graph first. As you can see, this white square is the IMU chip, and for the gesture like we detect, what really happened is to let the chip rotate along the y-axis. So we can see like as pitch. And here is and for the vertical line is a value for the pitch. And as the people move their head up and lower, and the value of pitch will change as the time passed. So what we do is like, as you can see, the yellow line is a trace for the nodding. And if we detect there's a negative pitch value lower than some threshold that we set it here, and then we will start to collect the pitch value for the following several seconds and find the highest value, and then we will get the difference between these two. We call this difference value, and then we will get the threshold to compare. If it's larger or equal to the threshold like we set it, we will say, okay, it's our IMU mode being triggered. And next, let's talk more about our gesture detection. First of all, let's look at the table here. This table is about the operating modes for our sensor, and here are so many modes, but what we pick is the 9-degree of freedom mode, because it's okay to receive the sensor signals about the oscillometer, magnetometer, gyroscope, and the absolute orientation. So it allows us to detect the user's gesture and at the same time able to get the accurate compass data for the following step. And next, let's talk about the data like we receive. Like the type of compass data we use is azimuth. So you can see the inner circle of this circle, like it uses the number from 0 to 630 degree to represent the direction. So it's easy for us to process the data for the following step. Next, let's talk more about building detection on the app set. So as you can see here, this spot represents the user's location. And once we get the bearing data, it will start to search along the bearing data by first move 2 meters to do the first search. And if we find there are any landmark in such a range, we will directly return the results. However, most of the time, like the building search will fail. So we will continue move along the building data to do the further search, something like this. And if we find any results, it will be returned. But if it didn't, like it will continue to do the further search. And if we find like we still couldn't find any results 80 meters away from user's location, and we will return some other results. So let's talk more about what's the value being returned. And first of all, as I mentioned, like all our final result is return in voice. And let's look at the picture. This is how the return looks like on the map view. And let's show how the value returned. If the landmark is within less than 30 meters away from the user, it will return like X is in front of you. If the building we detected is 30 to 80 meters away from the user, it will say X is close to you. And if the landmark is 80 meters away, like actually like out of our detected range, it will return like no building nearby. And yes, that's how the value being returned. And as let's say our further development is currently our IMU mode is okay to use, but we still have two aspects like words to get the better, able to improve to get better results. One is a compass accuracy. What I refer to is like if the user do some actions such as jumping, shaking head or running some crazy motion, and then to try to get the compass data. Most of the time, our compass data may not be that accuracy than the Euro. So we will try to consider some solution. Yeah, we will try to find some solution to make the compass keep accurate, even when after some like crazy action. And next is to get a better state estimation. What happen is like when we do some certain search, we might find there are more than one landmarks in our certain search. So we need to use more parameters that we get from the JSON package to better decide which one has a higher possibility, like is the building like really in front of the user, to make our results more accurate. Next, let me show you guys our final product. So this is how our final product look like, and we will include all our chips in the black box, and the black box will attach on the side of any sunglasses, and because it can easily remove and also it's very light, so it's okay to take out or just wear the sunglasses as usual. And on the left side, on the right side, this is how our app look like as we successfully Bluetooth impaired, and it will return some data about what's the mode right now, and also relative data, something like bearing data. And finally, it will return the results. I mean, the user's position and the detected landmark on our map on the center. And here is it. Now let's see a demo. So what happened, like, or how do we really view it and use it?
UPS store is in front of you. Albertsons is in front of you. UPS store is close to you. Albertsons is close to you. No building nearby.
So that's it. And Okay. Previous. Thanks for the Professor Yoga, TA Adi, TA Kyle, and the support from Qualum, and thank you very much. And any questions? Anybody?
Did you have any issues with false positives while you were trying to nod your head, like when you're walking or anything? And how did you fix it?
Wait, well, can you repeat the first sentence?
Did you have any issues with false positives, like 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 the glasses thinking you're nodding your head when it wasn't, when you weren't?
Do you mean like any problem on detecting the nod gesture?
Yes.
Oh, something is like, cause let me think how to say that. Oh, sometimes it's like when people try to finish their nods, but they spend like they are too slow or too quick. So at this moment, we couldn't successfully, we couldn't like really calculate, we couldn't, if it's too slow, like we couldn't get the high value higher enough. So like we will consider this difference is not, it is smaller than a threshold. So it will not be considered as the gesture we want. But if the user like they nodding like too quickly, so because like as I mentioned, like after I detect the negative pitch value, I will start to collect and get and to figure out the high-res data. But the data like we're collecting at that moment is based on some like time with some time step. So like if you nod your head too quickly, so maybe we will lose to capture that higher value, I mean the highest value we want to get. And that moment we will find like, oh, seems the threshold is not high, the difference we get is not high enough, and then it will be considered as, okay, it's not twice nodding. And also sometimes, because we set a negative value to start to collect the following data, but sometimes it's like, some people like they may like lower their head not that much, but they will hide their head like pretty much. But at this moment, the data may not be captured because like the users like lower their head, the value is not small enough. So it will not be considered as start to nod. So even will not get the difference to consider whether it's nodding or not. So this is some problem like we met when we try to measure the nodding head. Yeah. Do I answer your question?
Yeah, thank you.
Uh-huh.
Okay, if there are no questions, anyone else? All right, guys, so let's move on. Let's go to true posture next.
All right.
Hi, can you hear me?
Yes.
Hello, great. Hi, Tom. Shall I begin?
Let's go.
Okay, great. Hi, guys. We are the True Posture team. And I'm Jiyu Zhou. I'm responsible for the data analysis.
I'm Yingqiu Jiang. I'm mainly responsible for hardware design and setup of the project. So here's some basic project background. Traditionally, surgeons must do microsurgeries like eye surgeries in a hunched posture because they need to look closely into the microscope. However, surgeons have reported back and neck pain after doing several surgeries continuously in one day. So Alcon True Vision's solution to this problem is the innovative heads-up three-dimensional imaging technology. Surgeons can now do microsurgeries while sitting straight, by looking at the monitoring front. The goal of our project is to quantify the muscle fatigue level difference between the hunched and the straight posture by capturing EMG signal from back and neck muscles. So what is EMG? EMG stands for electromyography. It is an electrodiagnostic medicine technique for evaluating and recording electrical activity produced by skeleton muscles. Due to the recruitment of motor units, the EMG signal amplitude shows an increase, whereas the frequency-based mean or median frequency of the total power spectrum shows a decrease of the contraction time. As you can see here in the graph, the median and the mean frequency are fast Fourier transform based, and they are from the total power spectrum. So there are 4 different cases that can be distinguished from muscle fatigue. And in our project, we only focus on the number 3 here. If the EMG amplitude increase and the spectrum shifts to the left. So in our project, we used 3 different metrics to determine muscle fatigue. Amplitude increase, median frequency decrease, and the frequency domain curve shifts to the left. And in our project, we mainly focus on the number 3 here. Frequency domain shifts to the left. And the reason for these changes is that the conduction velocity of the motor actions potentials on the muscle membrane decrease.
Now let me introduce the experiment design. In our experiment, we focus on 3 parts of the muscles. The first one is the multifidus, the lower back muscle. The second one is the transversalis, the upper back muscle. And the third one is the trapezius discendens, the shoulder muscles. Due to limited time and resource in this period of time, in this project, now we only focused on the lower back muscles, which is most commonly reported by office workers and doctors with pain issues. So today, the result we present are the data collected from the multifidus, the lower back muscles. For our experiment format, we collect EMG signal data from 6 sensors simultaneously. 3 sensors on each side, so there are 6 sensors in total. For both straight and hunched, we will hold the posture for 30 minutes and collect the data to see how much muscle fatigue is accumulated in a period of time. Here are the 2 postures we use to simulate the microsurgery. The left one is a straight posture, and the right one is a hunch posture. Here are some metrics to quantify muscle fatigue. Before that, I would like to introduce a concept. It's called frequency distribution, or we can call it amplitude spectrum. It is used to describe the power of frequency. It's used to describe the power of the signal in different frequency range. And the first metric we use is full width at half maximum, FWHM, the width of a spectrum curve measured between those points on the y-axis, which are the maximum amplitude. And the second one is the median frequency. We use the frequency after we eliminate the noise signals.
Now I'm going to introduce the hardware part of the project. This is the general hardware block diagram of our project. As you can see here, we have all 6 EMG sensors interfaced with the STM32 microcontroller with analog input. And we have the Bluetooth module that allows wireless data transmission. And the the board also draws power from a power bank. So we separated the power pins and the data pins from the USB interface so that it protects the user from the risk of a current surge. This is the STM32 microcontroller we used. We choose this microcontroller because it has enough ADC channels that we need. This is the EMG sensor that we used. It's called myaware muscle sensor, and it has two output modes, rectified and raw signal. In this project, we used a raw EMG signal so that we can analyze the frequency information. This is the PCB layout and the final PCB. The top part of the PCB is basically used for power supply and data transmission. The lower part of the PCB, in the lower part of the PCB, we expose all the pins we need. The software debugging pins, power supply pins for the EMG sensors, ground pins, and analog input pins.
Now, let me introduce our last part, the signal analysis. In this project, all the signals are processed through MATLAB script. There are basically 5 steps in this experiment. The first one is to sanitize the raw data. From here, you can observe a noise point in the raw signal data. From our observation, the noise rate in the experiment is about 1 out of a million, so we can simply delete it or ignore it. The second step is to generate the amplitude spectrum using fast Fourier transformation. The third step is to fit the amplitude spectrum, then calculate the full width at half maximum, the FWHM. And the fourth step here is to examine the frequency shifting trend through the change of FWHM. And the last step, which is kind of optional, is to eliminate the failed dataset. Here's a sample for the failed dataset. It can be caused by failed connection or some other hardware issues because the hardware is not reliable sometimes. Let's go with more details. Yeah, here is the raw signal. The left one is the original raw signal, which is voltage related and it's collected from the malware EMG sensors. And right side is the amplitude and the scaled raw signal. The right side diagram is plotted out from the left side original signal data. Here is the frequency distribution, the amplitude spectrum. To see the shifting trend of the frequency, we generate the amplitude spectrum graph for every second in the 30 minutes period. From here, you can see the blue line is the amplitude spectrum, and the orange line here is the best fitting curve for the amplitude spectrum. We then calculate the full width at half maximum. It is marked as the half width here, which is 49 Hz. We record the FWHM of each second and plot them out to see the final trend of frequency shifting. Now let's see the result. Yeah, this is a graph after we plotting out all the FWHM in the 30 minutes period. And the slopes of the linear fitting are recorded to show frequency shifting trends. From here, you can see the shifting trends or linear fitting, the slope of it is kind of positive, which means muscle doesn't get really fatigued in this period of time. After we plot out all the slopes we received from previous steps, we receive this diagram. The blue circles here are for straight postures, and the orange circles here are for hunched postures. We can see the average slopes of the straight posture is about 0.0046, which is positive. And for the average slopes of the hunched postures, it's about negative 0.0028. We can say it's negative. When the slope is negative, it means the muscles can get more fatigue. From this diagram, we can see some obvious difference between two postures. Now I believe we can make a conclusion. The straight posture slopes are almost positive, and the hunch posture slopes are mostly negative, which means straight posture may rarely cause the lower back muscles to be fatigued. With the head-up posture, surgeons can better protect their lower back muscles in the surgery. Now, let me show you a video to better know our experiment.
Hi guys, we are the True Posture team. I'm Jiyu Zhou. I'm Dom Jiang.
First, we want to show you how EMG signal respond to intense muscle movements. For example, now we are exercising bicep, and you can see the EMG signal.
In this project, we focus on the lower back muscles.
And right now we are seeing the sitting straight posture. This is the hunched posture.
The next step is about the signal processing with the MATLAB. The function of this MATLAB script is to extract data from the original text file. The fast Fourier transform results will be generated, and the full width at half maximum values will be calculated to show the shifting trend of frequency. After plot out all the slopes in one diagram, you can obviously see the fatigue level difference between two postures and make a conclusion. That's all for us. We want to thanks to our sponsor, Alcon Tuition, our instructor, Dr. Yogananda Isukapali, and our TAs, Adi and Kai. Thank you, guys. Any question?
So I have a question about the frequency shift. If you go back to the conclusion slide.
Sure, no problem. It's stuck a bit.
The one before with the plot.
Yeah.
Yeah. So, oh, sorry, the one before, the one with the plot.
Yeah, no problem. Yeah. It's a little bit stuck. Yeah, got it.
So how much, so it looks clear that there's the red and the blue separation in the two. How much does the frequency shift have to be for you to be able to deterministically say that there was a muscle fatigue? Because I'm looking at the numbers here, right? The slopes.
Yeah.
And the slopes are very small. It looks like.
Really small. Yeah. Yeah, you can see in this project, we mainly measure the EMG signal for fixed postures. Actually, for all the muscles on your body, if you keep a fixed posture, it doesn't get really fatigued, as all the pain issues are caused by long-term fixed postures. Like for a bicep muscle, when we exercise like playing basketball, it may get really fatigued after a period of time of exercising. But for fixed postures, like the muscles on your back, especially lower back, for sitting like hours or a period of time, it may not get really fatigued. All the pain issues are caused by the accumulation of this kind of small fatigues. So even if it is really small, we can still see the difference between them. And in this project, our main purpose is to find if there is really difference between these two postures. And that's why it's really small. And although it's really small, it means something very important. Yeah.
Sure.
All right. Thank you.
All right. Thank you, guys. Thank you for watching.
Thank you, guys.
Hello, we are Safe Vision.
I'm Nathan Bornfriend.
I'm Rick Frank.
Hey, I'm Steven Landis.
And I'm Willie too.
For our Capstone project, we partnered with True Vision Alcon, who helped surgeons during operation by providing 3D surgical visualization. This is captured with a robotic stereoscopic digital microscope that they've developed. The microscope is supported at the end of a universal robotics arm with a max payload of 5 kilograms. Here you can see the head of the microscope is attached to the end of the arm. The arm has 6 degrees of freedom, which adds a lot of complexity to the movement. There are 3 operation modes, the first being free drive, where the user controls the arm by applying torque to the head of the arm. Second, remote control, where a user controls the arm through another device. And finally, automatic mode, where a set of pre-planned movements are automatically executed. The arm is unaware of surroundings, including doctors and equipment, and this may lead to accidental collision. Therefore, our goal is to prevent these collisions from happening. Here is an example of the arm being used in an operation room. The arm is being controlled through the free drive mode, and the screen portrays an image captured by the microscope. The doctor is focused on the screen and the patient, and therefore may not be 100% aware of the arm's surroundings, and this may lead to collision. Given this environment, our system must prevent object collision and safely stop the arm, which can move up to 0.8 meters per second. It must also move predictably, as the doctor must be in control of all movement in the operation room. All parts must follow medical guidelines, and it must weigh less than 1 kilogram, as the arm can support up to 5 kilograms, and the microscope weighs roughly 4 kilograms. Our proposed solution is to use distance sensors to detect objects in the direction of movement, as well as using a model of the arm to prevent self-collision. After the arm is stopped, we have to ensure safe conditions by checking for obstacles in the next direction of movement before resuming.
Here we have our overall system schematic for the project. It's divided into 2 main parts, the hardware and the software, with the hardware focused on the microcontroller getting the data from the optical distance sensor and sending it to our software system through UR, where the software is focused on the object detection, where it communicates to our universal robotic arm through real-time data exchange protocol to get the arm data and determine whether to stop the arm or not, depending on the arm data and the sensor data. So now we'll focus more on the hardware component. Here's the hardware schematic again. You can see there's 4 different I2C buses that's each connected to a set of optical distance sensors. And for the microcontroller, we decided to use the STM32F7 processor, which is a high-performance chip based on the ARM Cortex-M7. We decided to use the chip because due to our lack of dependency on battery, and since there are external power sources available, and we wanted to have more performance in an effort to help limit the processing time between getting the sensor data to sending it out to our software system through UR. As you can see here, the microcontroller have 4 different I2C buses that can help us separate out the sensor. So we'll talk more about later, but the sensor that we're using are in the breakout board form. So the pull resistors are still attached. The independent I2C buses help us prevent them from closing together, and which will produce a lower pull resistance for each bus that can result in overdrawing current through the devices and overheat. The microcontroller also provides UR communication that is connected to a UR converter, as shown by the bottom right, and to USB, where the USB is connected to a computer that's running our software system to send our sensor data into. Lastly, we use the ST-Link debugger to program the chip.
For the sensors that we choose to use, we chose to use the VL series time of flight sensors made by ST Microelectronics. They are class 1 optical sensors. That means they use infrared light to measure physical distances, thus being safe for the eyes. This is especially important for our purpose because we don't want to damage our patients' eyes during surgery. The measurement latency for these sensors is about 20 milliseconds, and the accuracy distance, the sensors are accurate at distances between 2.5 centimeters to about 80 centimeters. We measured these numbers experimentally. We found that closer than 2.5 centimeters, the sensor readings tend to bottom out, while at about more than 80 centimeters, the measurements were wildly inconsistent. The sensors also have a 25-degree field of view, which looks a bit like a narrow cone. Hence, we need so many sensors, about 30 of them, all over the arm to get a complete coverage of the arm's environment. We communicate with these sensors using I²C, and because we have so many sensors, we chose to use shielded wire to connect the sensors to the PCB to minimize any sort of crosstalk and interference. To mount the sensors on the arm, we designed and 3D printed 3 different types of mounts. These mounts correspond to different parts of the arm and head that the sensors are attached to. We attach these sensors to the arm using mounting putty, specifically because we're in the prototyping phase. This mounting putty is strong enough to adhere the sensors to the arm during motion, but they're also easy enough to take off without residue. So that we can move them around the arm freely. We also use zip ties to attach the shielded wire to the arms so that we can minimize the downward force on the mounts because the wires are very long and heavy. Here we have 2 perspectives of the CAD model of the robotic arm with the microscope head on it and also our PCB. The red dots on the arm signify sensor placements where we chose to put our sensors on the arm. Unfortunately, since we were unable to actually physically test these placements, there might still be blind spots we have not accounted for. This is our PCB that we designed. The picture is our final printed PCB. This PCB is a 4-layer PCB and it is about 6 inches by 7 inches. This PCB is fairly large with a lot of extra space, but we had to make it this large because of the headers around the edge of the board. Each of these headers is where all the sensors plug into, and in order to actually get to the headers to plug them in, we had to lay them out at the edges of the board, hence the large size. The PCB has 2 distinct power sources. One primary power source is the USB connection, and it is responsible for powering all the onboard PCB components, such as the STM32 processor. Furthermore, we have a secondary power source from a 5-volt 2-amp wall adapter that plugs into a barrel jack at the top of the PCB. This is responsible for powering all the sensors at the edge of the board, since the USB connection was not enough to supply power for the entire board and the sensors. Furthermore, although we're only using about 30 sensors, there's room for 36 sensors on the PCB in case we needed extra room for sensor expansion.
Here we have our microcontroller software workflow. It's pretty simple. We first have to initialize all the peripherals like UR and I²C. Next, we set up all the sensor devices, do I²C communication to all the sensor to set up the addresses and make sure we're getting all the data correctly. Next, we go into a cycle of reading the sensor data to I²C and transmitting those data to our software system to UR. Each cycle, there's 15 to 25 millisecond delay, depending on the mode of sensor that we're using. But those delay are required since any delay less than that would prevent the distance sensor from collecting the data correctly. Next, we'll focus on the software components.
Yeah, this is an overview of how our software works. So looking in the center, this is object detection. That's the core of our application. What this does is it takes a lot of information, such as sensor distances and the angles and angular velocities of each of the joints, and uses that information to determine if the arm is about to collide with an object and set the arm's mode. So to read some of that information in, if you look at the top left, you can see the sensor data block, which passes information through UART to the serial port communication that then passes sensor distances to object detection. Communicating with the arm is a little more complicated because we have to both send and receive data. Some of the information we send is the operating modes for the arm, and some of the information we receive are the joints and velocities, or yeah, the angles and velocities of each of the joints. We get that information using the RTD connection through the control system. We also use all that information, the sensor distances and angular joint angles and velocities, to visualize the arm and all the sensors. And finally, we have an Android app that we can use to remotely view and control the arm.
Our software is mainly dependent on the universal robotic arm that was provided to us by TrueVision and Alcon. The software uses a real-time data exchange protocol to communicate with the arm to receive the data, such as the joint angle and velocity. And within the arm, it uses the UR script programming language to control its logic. And in times where we don't have the physical arm available, we use the Polyscope UR simulator for our development, which provides enough information as the physical arm for development.
Here's a picture showing our visualization. On the right, we have Polyscope showing the state of the arm, and on the left, you can see our visualization with the arm in the same position. However, our visualization has some additional information, such as the head of the arm that's drawn. Also looking, you can see a bunch of red lines that are crossing the screen. Each of these lines corresponds to a sensor, pointing in the direction that it's trying to sense data. If the sensor detects an object, you can see a red circle appears, and the red line is drawn shorter to indicate the distance. If the object is detected far away, the circle is going to be large because the cross-section of the detection cone is going to be large. However, if the object is detected very near to the sensor, that circle is going to be small because the cross-section of this cone is smaller. We can also place obstacles in our simulation, such as the slightly transparent cube in kind of the back of the simulation. And looking at the top left, we also have a few control boxes and panels. So we can look at sensor data to make sure we're reading in the correct values. We can also toggle on obstacles, and we can manually set the control mode of the arm. One of the features we use to give more accurate results is sensor enabling, which means we only stop the arm if sensors that are moving forward or moving in the direction of the normal detect an object that's close. And we ignore all other sensors because they're not in danger of running into an obstacle. So in this picture right here, if you look on the right in Polyscope, the right arrow is grayed out, which means that the head of the arm is currently moving to the right. If you look on the left, you can see that some of the sensors are red, which means that they're disabled, but some of the sensors are drawn green, which means that they're currently enabled. And if they detect an object that is close, the arm will stop. However, sometimes just using sensor data isn't enough to see if the arm should stop. There are a few scenarios where the sensors get blocked by the arm itself. In that case, we can use the model of the arm directly to determine if the arm is about to run into itself. How we do that is we model each segment of the arm as a rectangular prism. And if any of those rectangular prisms intersect, that means the arm is about to run into itself and it should probably stop. If the arm stops due to rectangular prisms intersecting, we wait until the torque center, we use the torque sensor to determine if any of the rectangular prisms are moving apart from each other before resuming motion safely.
We created an Android app to allow for remote control of the robotic arm and to get feedback from the onboard Safe Vision system. The app communicates with the Windows host machine via a TCP client. The Windows host machine has a server created using WinSock. The server sends the client arm joint positions and sensor data so that the arm can model in the app, so the app can model a OpenGL simulation of the arm in real time. The Android app also allows for control of the arm by giving the user independent control of each of the 6 joints of the arm. In case of conflicting commands between local and remote, local control will always take priority to prevent any sort of mishaps from occurring.
Here are our 3 biggest challenges we faced during the development of Safe Vision. First, we had to limit sensors to those in the direction of motion. In addition, sensors that detect the arm itself should be ignored. In the top right image, we have an example where the sensor is detecting a part of the arm that it will never collide with. And in the bottom right, we see that the sensor is still useful in other situations. Second, given the speed of the arm and distance range of the sensors, we have roughly half a second to stop the arm. Therefore, we had to optimize hardware and software for speed. Finally, due to COVID-19, we had to work remotely, which forced us to focus on software. We attempted to simulate physical testing with situation tests and increase the use of Safe Vision with an Android app. Here is a demo of Safe Vision.
The following video is an in-person test of the collision detection system. We have two sensors on each side of the head. When they detect a hand, the arm slows to a stop, and when no obstacles are detected, the arm smoothly accelerates and resumes its movement. This next section demonstrates situation tests. Because of COVID-19, we couldn't do any more in-person tests, so we designed virtual tests to check our collision system. Even though these tests are virtual, the interfaces for the Universal Robotics Simulator and the real arm are identical, making it easy to switch between the two. Each situation test has 3 steps. First, the arm moves to its starting position. Then, obstacles are placed in the simulation, and finally, the arm moves to its end position and may or may not stop. In the test just shown, the arm correctly stopped because a sensor near the head of the arm detected a nearby obstacle. In this next test, the arm starts very close to an obstacle. However, because the arm moves away from the obstacle and isn't in danger of colliding, the arm doesn't stop. This next test demonstrates how the arm stops before colliding with itself. This test doesn't need sensor data because it uses the simulated model of the arm. When the base and head of the arm get too close, the arm stops. Finally, here's a demo of the Safe Vision Android app. There are 3 windows on screen. The left window is Polyscope, which is the UR arm simulator. The right window is our visualization program, and the phone shows the app. Before using the app to control the arm, users need to submit the correct IP address, port, and password. This brings the user to the control page. The top shows a visualization of the arm and its sensors. Right under that, there are 3 radio buttons that show the arm's operating mode. And under that, there are 6 sliders controlling the arm's joint angles. When users change joint angles, all 3 visualizations update together, which means that data is being passed correctly, from the app to our visualization through an HTTP server, and then to the arm through a TCP connection. When the user isn't moving a joint, the arm goes into stop mode, which can be seen both in the app and in the visualization. Even when the user controls the arm through the app, collision detection is still enabled, which means the arm stops before colliding with obstacles. This app, with a password-protected login, visualization, and collision detection, enables people to safely view and control the arm from remote locations. The following video.
We'd like to thank everyone who help us with the project. Especially would like to thank Yupei and Patrick from True Vision Outcome, and Professor Yoga, along with our TAs, Kyles and Aditya, for making this project possible. We're open to any questions.
I had a question.
Yeah.
So in a hospital environment, you would probably be covering the microscope with plastic to keep it hermetically sealed. So does the sensor still work in those circumstances?
I don't think we thought about that, to be honest.
Yeah, I don't think we've tested this. It was more of a prototype or a proof of concept to prove whether we could stop the arm, and we would have to adapt, I guess, once it actually went through.
That's a good point, though. Thank you for the question.
I have a question. This is Yupei from Alcom. So if you guys have more time, what else do you guys think you can improve other than testing the hardware on the arm, which did not happen, unfortunately, due to the COVID-19? But other than that, what else do you guys think there's place for improvement?
So right now, with our PCB, there are some errors that we can, well, hardware obviously, like more PCB testing to make it better, because right now there's some bugs with it. But other than that, I think we want to optimize the the algorithm for the Android app to the Safe Vision program, since the control, as you saw in the demo video, is not very smooth. So we probably want to update that. But other than that, we really need the physical arm to be able to further the development of Safe Vision.
We'd also add more features to the app because the app is pretty bare bones right now.
Thank you. You guys did a good job.
Thank you,
Thank
Yupei.
you.
Thank you.
Thank you.
Okay, thank you, guys. If there are no further questions, we can go to the next project, Scopen.
You can start for me.
Okay. Hello, everyone. We are Team Scopen. We will give our capstone project right now. So before get started, let's introduce ourselves.
Hi, I'm Byron Aguilar. I was the team leader of the project. I also helped develop some parts of it, such as the analog front end and the firmware design.
Hello, everyone. I'm Boning. Basically, I'm in charge of system design, board layout, firmware, software, and board assembly.
Hello, everyone. I'm Caesar. I'm in charge of AFE design, power management, and firmware for the DAC interface.
Okay, first, we want to give you guys a little bit background why we want to build such a project. So I guess you guys all have the experience of using an oscilloscope in the past 4 years. I'm not sure about you guys' experience of using an oscilloscope, but for me, I think using an oscilloscope is not very easy. First, because we always need to go to the lab to access the device, which is kind of inconvenient, especially during the COVID-19 situation. It's getting harder even. The second thing is oscilloscope usually take a lot of space on my table. So, using an oscilloscope with my laptop, usually I don't have enough space for something else. The third thing is if you want to get one at your home, if you're not a hardcore developer, like a hardcore engineer, probably you will not, because that's super expensive and also kind of inconvenient. So we are thinking whether we can solve this problem. And the first question we ask us is, for students and hobbyists, do we really need a huge and expensive one? What are the key features we actually need for students, right? So our answer toward this, we believe there are 4 important things. First, it should be able to detect waveform. After all, that's an oscilloscope. If you can't do that, that's not, right? Second, it should be portable. What do we mean portable is, what if you can put that in your pocket, in a folder, in a bag? That would be so convenient. You don't need to go to school anymore. Even during COVID-19, you can debug that at your home. The third thing, we want it to be intuitive. What do we mean intuitive? Because we believe 90% of the features in oscilloscope, in the real professional oscilloscope, we are actually not using it. For our personal project, the frequency are usually pretty low, and a lot of features actually just be wasted. So the fourth thing we believe is the most important thing is it should be affordable. For students, you don't want to spend $700 on a device and just use it once or twice per year. So eventually, we want to build a device that converts your workbench from the top to the bottom. Our solution to the problem we proposed is Scopen, a wireless oscilloscope, the power of an oscilloscope in a pen. So before going into the technical details, let's watch a demo video to get familiar with what it's capable of.
Yeah, our project structure branches out into 4 categories. We have hardware design, where we can find the analog front end and various systems. The firmware design encompasses the waveform sampling method we developed and thread manager. Software design handles communication between Scopin and the user's device. And the industrial design focuses on the physical appearance of our product. Expanding on the hardware design, the analog front end handles the initial input and converts it to an acceptable differential signal. The STM32 microcontroller is responsible for sampling this differential signal, sending the data to an external memory, and later moving the data to the Wi-Fi module. As mentioned before, the AFE's purpose is to handle the initial analog signal and massage it enough to be sampled by the ADCs. In order to be able to handle a wide variety of voltage signals and amplitudes, we needed a robust design that can ensure everything is accounted for. The input first goes through a stage in which it will be attenuated or not. If it is attenuated, the signal's amplitude is heavily decreased, and this is how we are able to measure the larger signals. After the attenuation stage, the signal goes through an amplifying stage that increases the signal's amplitude to fit the max sampling range of the ADC. This way, we take advantage of the ADC's full capabilities. The last stage is for the input to be converted from a single-ended signal into a differential one. The ADCs are able to measure single-ended signals, but in order to smooth out potential disturbances, having a differential signal works best. A few of the challenges we faced for the AFE design are the following. We needed to make sure that the impedance of one stage wouldn't distort our signal, so we selected components with high input impedances and placed buffers in between stages to ensure our stages are isolated from one another. Designing the gain stage was quite difficult as well. We knew we needed multiple gain settings to account for the various signals. Our solution was to use a VGA, or variable gain amplifier, but finding a VGA that provided a variety of gain values was quite difficult, but we ultimately found one that was perfect for the task, where we could control the gain using the DAC found in the STM32.
The main purpose of our hardware system is to sample and send data to the user quickly. We also wanted to implement a feature to change oscilloscope settings with simple touch gestures from the pen. To achieve the sampling, we needed fast ADCs. This is taken care of by the STM32 G4 microcontroller. Once an oscilloscope obtains data points, often it obtains a large amount of data points. So this data has to be buffered into external memory before being sent out through Wi-Fi. Lastly, to implement our wireless feature, we needed a Wi-Fi module. In this case, we chose the ESP32 Pico so that we could implement that feature. Some of the challenges we faced with designing this system was part selection. In particular, for the microcontroller, we needed a part that had a small package but had fast ADCs. Unfortunately, not many microcontrollers on the market have this combination of features. So to compromise, we chose a microcontroller with 4 medium-speed ADCs that could be combined together to increase our sampling rate. For the memory selection, we had to choose a part that had big enough storage, had a small package, but still was easy to solder. Luckily, we found the IS6 static RAM module, which fit our criteria. Now you may notice the theme of our challenges and our part selection is that we wanted something small. We needed something small. This is because our goal was to fit this system into the form factor of a pen. That is why our system had to be compact, and that is why we designed our 6-layer board. On the screen right now, you should see the 6 layers that we used. As you can see, the traces are small and the routing is compact. This is all to fit everything into one single PCB. And the 3D render here, you can see like all the components, how they fit nice and compact onto the board. Overall, the length is 2.45 inches in length and 0.73 inches in width. To put this in perspective, this board is no bigger than your average stick of gum, so it's quite small. But to achieve this size, we couldn't just rely on one side of the board. We also had to place components on the other side of the board. So on the other side of the board, we also have more passives and ICs where to incorporate our entire hardware system into one single small PCB that can fit inside a pen. And then the end result was this small board, and we were happy with the end result, and it fit our project goals perfectly.
Okay, so next I'll talk about firmware design. Basically, the firmware can be divided into two parts. The first part is STM32G4. That's the core controller of our system, basically handling all of the peripherals like touch sensor, battery management, handle the sampling. The other part is the ESP32. Basically, that's a Wi-Fi controller. This controller functions as the bridge between the core controller and our software. We will talk about that later. So the first thing I want to show you guys is the firmware architecture of our project. Basically, left and right, there are two parts. Let's look at the left first. From the bottom, that's the lowest level of our software, basically, firmware, I should say. So our project, the STM32G4 is a Cortex M4 architecture controller. This is important because it's free RTOS. We will talk about it later. Actually, use this part. So also for the driver level, we use a lot of STM32 Hall drivers library, including SRAM, ADC, SPI, DAC, a lot of things. But some peripherals, for example, a touch sensor requires special features. For example, I2C restart feature. But this feature is not enabled by the STM32 Hall library. So the way we solve that, we actually develop our own library based on STM32LL library. LL stands for low level. It's actually a wrapper for all of the registers. So that's basically the bottom level, the driver level. The second layer is basically the peripheral layer, we call it. So basically, we can see the touch sensor, we can see an analog front end, we can see battery management. And another thing that across this layer is a free RTOS. RTOS means real-time operating system. The reason we need that is because we want to manage different threads. And on the top layer, the highest one, you can see we are running actually 5 threads in the same time. So 3 of them are handling data transmission, sending and receiving. The other 2 are handling internal events. For example, if you send something to the controller, you need to be able to run the command. Another thing is handling the user input. So on the right-hand side, that's the ESP part. ESP, we actually developed the ESP using Arduino. So the overall, the stacks looks a little bit easier, but actually that's not the case when you really do the development work. We're going to talk about that. So several challenges we are facing at this stage. The first challenge is how can we make sure the ADC sampled in equal space time span? That's super hard. You probably say, okay, how about set a timer and use interrupt? Every time you trigger the interrupt, inside the interrupt, you call the ADC. You say, okay, start sampling. But there's a problem. We need to consider about the context switching time of the interrupt. Even though it's super fast, but that time is actually unpredictable. Because for example, you're running a routine right now and the interrupt happened, you need to jump to another routine. That part of time should be considered. So our solution toward this problem is we are using the high resolution timer on our system. How does this work? You can actually set several compare values to the high resolution timer. And when the counter is running, it will keep comparing to the compare value. If it is the same as the compare value, it will trigger something. For our case, we will trigger the ADC sampling. So the way how it works, we set a period for the high resolution timer, divide the period by 4, so that we can make sure the ADC are triggered in equal space time span. So that's the first part. After the ADC is done sampling, it will tell the CPU, basically say, hey, dude, I'm done. What are you gonna do? Whatever. You're gonna handle this, right? So the CPU will take over right now and tell the DMA to migrate the data from the ADC to external memory. The reason that we are not asking the CPU to handle the data transmission, because this will take a lot of CPU time. But CPU can see with the help of DMA, CPU can simply say, okay, help me move the data from here to here, and I will now take care of the rest. Just tell me when you're done. So in this way, we are offloading the CPU time, basically. Use it for a lot of other things. That's the first part. Second challenge is the thread management. Like I mentioned, we are running 5 things together in the same time. How can that be possible on a controller only have 1 single core? That's why we use RTOS. RTOS is an operating system, so it manages the threads for us. But even though we can run 5 things together in the same time, there are still other problems. For example, when the data sending and command sending thread are trying to send things in the same time, what's that going to happen? For example, they're all trying to access the SPI. Is there going to be a problem? The answer is yes. There's going to be a race condition. And if race condition happen, probably it will corrupt the data, or probably it will crash the system. That's definitely not what we want. So how could we solve that? We actually use a semaphore. Semaphore actually functions like a lock. So every time you are trying to send something, you lock the semaphore. So if another thread is also coming right now, say I want to send something to the spy, it will also try to lock. But if the spy is already locked, it will wait for a while and come back again to check whether it's unlocked. That's the idea. Another thing we would like to mention for inter-thread communication, we are actually using a queue. So with the queue, we also have the race condition issue. The way we solve that also use semaphore. But the interesting part here is we use two semaphore. The reason is semaphore has an associated counter inside. So we can actually use the counter to represent how many empty slots we have, how many available commands we need to send. In that way, there are two semaphore, solve the race condition, and also make the code to be manageable, clean, and structured. So for the ESP challenge, Byron can talk about that.
Right. So the goal of our firmware in this stage is to create an interface between the user GUI and the microcontroller. And in this process, the ESP32 Wi-Fi module had to be as transparent as possible, meaning that it should only send the data from one end of the chain to the other without introducing any delays overhead. This was difficult to do because we had to implement various communication protocols, create our own communication format, and make sure that the upstream link and the downstream link were as fast and reliable as possible. Now I'll present how our communication worked. So first, the user connects to the Scopin wireless network. After that is done, the user interface sends a scan message, which the Scopin picks up and replies with its own network information. Using this network information, the user interface connects to the Scopin's TCP sockets, and then the user can start sending commands back and forth. So for example, to start sampling, the user interface sends a command through the TCP socket to the Wi-Fi module, and this command is forwarded via UART interface to the microcontroller. Now, we wanted our own communication format to make this as clean as possible. So first, between each communication, a header is sent. And in this header, it contains the data size and the data type. And once this header is received by the receiver sends an acknowledge back to the sender so the sender can send the remaining data forward. So once this, for example, this sample start command is received by the microcontroller begins sampling data and sending it upward through an SPI interface to the Wi-Fi module. And once the Wi-Fi module receives it, it just forwards it via another TCP socket upstream to the user interface. And in the user interface, it processes the data and displays it on the screen.
Okay, next we're gonna talk about the software design. Software design, we actually have two parts, but we will talk about only one. We're actually developing the desktop software and Android software together. But as Android software, we haven't tested it, so we will not mention too much here. So the only thing that is important about software design, I think, is the architecture. Even though there are a lot of details here, different class names, probably you can see that it's fine, it's not important. The only takeaway here is understand that there are 3 layers. There are 3 layers because we are trying to follow the model view controller design pattern, which makes our code more clean and manageable. So at the bottom, that's the model layer. The model layer basically handles the data structure, underlying data structure, and a low-level communication logic. Low-level logic is, for example, the communication, command parsing. So the layer in between, the red color one, that's the controller layer. Controller layer is just like we can say the bridge between the bottom and top. So on the top, that's the GUI layer, or say Viv layer. This layer handles everything you can see on the screen, every buttons, all the knobs. We actually use a super low-level swing library to draw out everything, to draw all the knobs line by line, because we want to make it look good. So another thing this layer handles is also the user input. When the user click a button, the logic here, the event actually triggered here. Another thing about software we want to mention is from the signal propagation perspective, when you receive some data, when you receive some command from the pin, it actually trigger an event at the bottom layer, and the signal propagate toward the top. If user clicks something on the software, the event actually happen on the top layer, and the signal propagate from the to the bottom. The last thing I want to mention is there are 2 squares that are not colored. You can see right color is sort of wireframe. These 2 are not classes. These two are actually interface. We design the interface because we want to enable the callback functions, and we also want to make our code to be more clean, more organized. Basically, that's the architecture part of our software. Next, I want to show you guys the interface. So you click scan, you can find the available pin in the network, connect to it, and you can click start. So here you are sampling the waveform. You can change the voltage division. You can change the time division. So basically, that's the interface of our software. Super simple, intuitive, with a sexy dark theme, which is kind of popular in recent years. So I would say that's really, really good. Next thing we want to show you guys, I guess Caesar going to talk about the industrial design.
Yeah, so the industrial design encompasses how we design the body shell for our product using Fusion 360 software. The biggest challenge was our lack of experience with 3D modeling. So creating a design that is both functional and appealing was quite difficult. And because we are 3D printing the shell, we had to take into account the durability of the material and make sure all the components fit inside the casing. We had to fit the PCB board, the embedded touch sensor board, the battery, and the steel tip while creating foundations for all of these components to secure them in place. Overall, we are extremely happy with the design, and this next video showcases our product.
Wait, actually, I can now switch to the next one. Okay. So I'll make a summary about our product. It supports 20-volt peak-to-peak voltage range, total length 5.9 inches. When you hold it, just like a marker in your hand. It also supports micro USB charging with the lithium-ion battery inside, which enables the portability, right? So the sampling, the input signal bandwidth, that's 5 megahertz. I would say it's definitely not high, but definitely enough for you guys. Trust me, for students, it's definitely enough for us. For most our personal project, it's probably the frequency even lower than 1 megahertz. Also, it has a touchpad on the pin, so you can interact with the pin, change the parameters, change the voltage division, time division easily, intuitively. Next, I want to compare the price with different products. So our pen only spent $120 in total for making one. By the way, that's why I mentioned, the reason I mentioned by making one is because if you are trying to sell this product, make this to be a massive production, it'll be way cheaper than this. So comparing our product, we can see the other two. Digilin, you guys are familiar. We all use this in our EC10 series class. It's portable, yes, but it's not wireless. It's still not portable enough, not convenient enough. The other one is WS2000. This one, we actually find it before rebuilding our product. But the thing is, they are super expensive, $300. And to be honest, if considering about spending $300 buying a pin-shaped oscilloscope without a good performance, I'd rather buy a Switch with Animal Crossing probably. It'll be way worth it because the pin-shaped scope pin is actually, their performance a little bit faster than ours, but actually not that fast. If you're a professional level user, you will not consider about that, probably spending a little bit more to buy a professional oscilloscope. So till right now, we covered up all of the details of our product. Next, I think Caesar, I think Byron gonna do the conclusion.
Yeah, so to conclude, I just want to give a special thanks to the people who helped us with our project, to our sponsors, Qualcomm, Veritech, and the UCSB College of Engineering. Also, special thanks to Professor Yoga, Adi, and Kyle for their guidance throughout this journey. Also, a special thanks to Leo for helping us film our demo video, and Jeff, who helped develop the Android application. But as Boning said, we couldn't fully test this, so we didn't include it in the presentation, but we still wanted to give an acknowledgement to his contribution. So are there any questions?
Are you guys selling any of these?
Not yet, not yet.
Not yet,
we still
not
have to
yet.
do
We are thinking
let's
about
move on
it.
a few bugs. Yeah.
Yeah.
Cool. What was the hardest part regarding the hardware design?
Hard part, I guess, is divided into two parts. For system part, because I work on the system part a lot. I guess the hardest thing is how to pack everything into such a small board. Especially, we also need to consider about some high speed, what I call high speed transmission, high speed wires. Like for example, when you sample ADC, you need to make them to be a differential pair. That's why we also use a differential amplifier in the first stage, actually. For AFE part, I guess Byron and Cedar can talk more about that.
Yeah, so for the AFE, like we have to make sure that there was like it could input a large amount of arbitrary waveforms as well as have low noise. So these were a lot of challenges that sometimes we overlooked, sometimes we couldn't accommodate for. So improving on that would be something that we would do in the next if we had more time.
Right. Other questions?